In the vast cosmos, there are enormous regions that seem strangely empty. These are vast stretches of space where little to nothing can be seen. Scientists call these regions cosmic voids, and they are some of the largest structures in the universe. The idea that such gigantic black spaces exist still amazes scientists. Could these be areas where the universe has not finished expanding, or maybe completely barren zones with no matter, no galaxies, and no energy at all? In this video, we take a closer look at the Booter's Void, one of the largest and most puzzling empty regions found in the universe. Before we start, tell us in the comments below where in the world you're watching from and what time it is there now. Get ready for an amazing cosmic journey. Cosmic voids, sometimes called dark spaces, are enormous regions of the universe that lie between the vast filaments, making up the largest cosmic structures. These voids contain very few galaxies, and in some cases, almost none at all. Even though they cover a huge volume of space, most galaxies do not live inside these voids. Instead, galaxies tend to cluster together under the pull of gravity, forming gigantic interconnected structures called galaxy filaments. The way voids develop over time is very different from the way the universe as a whole evolves. In these regions, there is a long stage in which the curvature of space itself dominates, and this prevents the creation of galaxy clusters and massive galaxies. Yet, even in their emptiest areas, voids are not completely without matter. They still hold a little more than about 15% of the average matter density of the universe. To the human eye, however, they look almost completely empty. On average, voids are extremely large, with diameters ranging from about 10 to 100 megaparsecs. That is roughly 30 to 300 million light-years across. The largest among them, which lack any rich superclusters of galaxies, are known as supervoids. These vast empty regions were first identified in the year 1978 by astronomers Stephen Gregory and Laird A. Thompson, who carried out their work at the Kitt Peak National Observatory in Arizona. Scientists believe voids were formed during the earliest moments after the Big Bang. They were shaped by what are called baryon acoustic oscillations, ripples in the hot plasma of the young universe. Matter collapsed in some places and compressed in others, leaving behind gaps that later expanded into voids. Tiny irregularities caused by quantum fluctuations in the very first fractions of a second of the universe slowly grew larger and larger. Regions that had slightly more matter collapsed more quickly under gravity, while the emptier regions stretched out into the vast cosmic voids. This process eventually produced the cosmic web, a gigantic foam-like pattern of filaments and voids that fills the entire universe. Interestingly, voids found in crowded regions of the universe are usually smaller, while those in less dense regions grow much larger. Voids also connect to one of the most important pieces of evidence for dark energy. They seem to line up with patterns in the cosmic microwave background, the faint glow left behind from the Big Bang. Because of what is called the Sachs-Wolf effect, the colder spots of this ancient light map tend to match the locations of voids, while the hotter spots match the dense filaments of galaxies. This happens because light travelling through these regions is stretched and shifted by gravity. Since the Sachs-Wolf effect becomes important only when radiation or dark energy dominates the universe, the presence of voids provides strong physical evidence that dark energy really exists. Astronomers describe the universe in terms of a few main components that together form the cosmic web. The emptiest parts are the voids themselves, which are generally spherical in shape and can reach up to 100 megaparsecs across. Then there are the walls, which contain the typical amount of matter for the universe. Walls can be broken down further into two main features: clusters, which are very dense zones where walls intersect, and filaments, which are the long branching strands of matter that can stretch across tens of megaparsecs. By comparison, voids have an average density less than 1/10 of the normal cosmic density. This is the working definition astronomers usually rely on, though there is no single agreed definition of what exactly qualifies as a void. When scientists describe density, they usually do it by counting the number of galaxies in a given volume of space, not by directly measuring the total mass contained there. The serious study of cosmic voids began in the middle of the 1970s. Redshift surveys, which measure how far away galaxies are by the stretching of their light, gave astronomers their first clear three-dimensional maps of the universe. In the year 1978, two separate teams of scientists identified the first superclusters and voids. These surveys were revolutionary because they added depth to the previously flat two-dimensional sky maps, which often looked overcrowded and confusing. Redshift data allowed astronomers to calculate the distances of galaxies more precisely, using Hubble's law, which relates redshift to the expansion of the universe. A timeline of discoveries shows how quickly the study of voids advanced. In the year 1961, astronomers first began to recognize very large structures in space, such as second-order clusters, a type of supercluster. In 1978, the first scientific papers describing voids were published, focusing on empty regions in front of the Coma and Abell 1367 clusters. In 1981, a huge void was found in the Boötes constellation. It was nearly 50 megaparsecs in diameter, though later calculations placed it closer to 34 megaparsecs. By 1983, computer simulations had become advanced enough to give reliable results about how galaxies and cosmic structures grow and evolve, offering new insights into the distribution of matter. In 1985, astronomers mapped the void and supercluster structures of the Perseus-Pisces region. In 1989, the Center for Astrophysics Redshift Survey revealed that enormous voids, sharp filaments, and massive walls actually dominate the structure of the cosmos. In 1991, the Las Campanas Redshift Survey confirmed that voids were not rare, but abundant throughout the universe. In 1995, astronomers compared different galaxy surveys and found that the same voids appeared no matter what sample of galaxies they studied. In the year 2001, the completion of the 2-degree field galaxy redshift survey added a very large number of new voids to the cosmic database. By 2009, data from the Sloan Digital Sky Survey, combined with earlier surveys, provided the most detailed and complete picture of the cosmic web ever achieved, showing in great detail how voids and filaments shape the universe. Astronomers have developed several different ways to search for cosmic voids using the results of large surveys of the universe. Even though there are many specific techniques, almost all of them fall into 3 main groups. The first group includes methods that try to find empty regions of space by looking at how galaxies are spread out and measuring local galaxy density. The second group includes methods that look at the shapes and patterns formed by dark matter, which are suggested by the way galaxies are arranged. The third group consists of methods that use the movement and instability of matter under gravity to locate voids by studying unstable points in the dark matter distribution. One of the earliest and most widely used techniques from the first group takes each galaxy listed in a catalogue and uses something called the nearest neighbour approximation. This method measures the cosmic density inside a spherical region whose radius is based on the distance to the third nearest galaxy. This technique was first introduced in the year 1997 by Elad and Pyron, who wanted to create a fast and reliable way of identifying voids. Once all these spherical regions are calculated, each sphere is expanded until the density inside it rises back to the average level expected in cosmic walls. One useful feature of voids is that their edges are very sharp and easy to identify. Inside the void, the density is only about 10% of the average, but as you move outward it climbs to about 20% at the boundary, and then quickly rises to 100% in the galaxy walls that surround the void. These boundaries allow scientists to divide space into 3 main zones: the dense filaments where galaxies cluster, the near-empty voids, and the overlapping regions between them. If a newly found void overlaps by more than 10% with another already known void, it is considered to be just a smaller part of the larger one. To be included in the official catalogues, voids must also have a minimum size of about 10 megaparsecs in radius, which ensures that random errors or small gaps in the data are not mistakenly counted as real voids. The second group of methods takes a very different approach. One important technique from this group is based on what is known as Voronoi tessellation. This process uses imaginary border particles to divide space into different regions depending on the contrast between high-density galaxy walls and the empty zones in between. This method was introduced in the year 2008 by Neyring, who wanted to create a way of finding voids without assuming any particular shape or using adjustable parameters. Because of this, the voids identified using this method are often more natural in shape and size. However, the method also has its weaknesses. It is sometimes criticized because it often identifies too many small or unimportant voids that may not matter much for larger studies. To address this, a rule can be added that only counts a void if the density inside it is at least 5 times lower than the average cosmic density. This same technique also allows the discovery of smaller voids inside larger ones, called subvoids, which raises questions about how exactly we should define what counts as a void. A well-known program called VID is based on this method, building on the earlier algorithm Zobov. The third group of methods is very different from both of the others. Instead of defining a void simply as an empty or low-density region where few galaxies exist, this method defines a void as a place where matter is actively flowing outward. In this way, voids are treated as regions where the distribution of matter is being shaped by the effects of dark energy. According to this idea, the centers of voids are considered the main sources of what is called the displacement field. This redefinition of voids was first introduced in the year 2009 by Lavaux and Wandelt, who created a method known as DIVA. The main goal of DIVA was to allow scientists to make exact calculations of the shapes and movements of voids in order to better understand how they change over time. Using DIVA, voids are classified into three main types: true voids, which are nearly empty, pancake voids, which are flattened structures, and filament voids, which are stretched and elongated. Another important strength of this method is that, even though it suffers from some of the same biases as other approaches, it is designed in such a way that those biases can be corrected with great accuracy, making its results much more trustworthy. Still, this method also has some drawbacks. For example, the voids it identifies are not always the same as those found with other techniques, which makes it difficult to compare results across different algorithms. Here's a rewritten version of your extract in simpler words, made more elaborate, more interesting, and with all numbers and dates written out fully in words. Voids have become an important tool in helping scientists understand the universe. They are not just empty spaces. They are like natural laboratories that allow researchers to test ideas about how the universe grows, changes, and evolves. By studying voids, astronomers have gained insights into some of the greatest mysteries of modern science, such as dark energy, the invisible force that seems to be pushing the universe to expand faster and faster. Our own home, the Milky Way galaxy, is located inside a cosmic void known as the KBC void. One of the most fascinating findings is that the universe cannot be explained without including dark energy. The existence of the largest known voids alongside the most massive galaxy clusters suggests that around 70% of the universe today is made up of dark energy. This agrees with information gathered from the cosmic microwave background, which is the faint afterglow of the Big Bang. Voids, acting like giant bubbles within the universe, are very sensitive to changes in the cosmos. Their shapes evolve partly because the universe itself is expanding. Since this cosmic acceleration is believed to be driven by dark energy, tracking how the shapes of voids change over long stretches of time can help refine or challenge existing models, such as the widely accepted lambda cold dark matter model, or more detailed versions like the quintessence plus cold dark matter model. This makes voids powerful tools for improving our understanding of how dark energy works. Voids are also closely linked to another strange particle, neutrinos. Neutrinos are incredibly tiny in mass and almost never interact with other matter. Because of this, they can move freely in and out of voids that are smaller than the average distance a neutrino typically travels before it collides with anything. This constant movement of neutrinos affects the size and distribution of voids. In the future, large surveys of the sky, such as those planned with the Euclid satellite, may be able to measure the combined mass of all neutrino types by comparing observed void patterns with theoretical predictions. Another reason voids are so interesting is that they contain a slightly different mix of galaxies and matter compared to other regions of the universe. This unusual composition supports the predictions of cold dark matter models, which suggest that galaxy formation is biased by the environment. In practice, this means that galaxies in voids form and evolve differently than galaxies in crowded cosmic neighborhoods. On a local scale, researchers have noticed that galaxies inside voids show differences in both their shapes and their light spectra, compared to galaxies that lie in denser regions, often referred to as the walls. One striking discovery is that voids contain a higher percentage of starburst galaxies. These are galaxies filled with young, hot stars that are forming at an unusually fast rate than galaxies located in denser walls. Voids also offer clues about one of the most puzzling forces in the cosmos, magnetic fields. A study in the year 2015 suggested that intergalactic space has a magnetic field of at least 10 raised to the power of -17 Gauss. This conclusion came from studying how powerful gamma rays, emitted by distant blazars, are deflected while travelling through voids. Such evidence supports the idea of primordial magnetogenesis, meaning that magnetic fields may have been created very early in the universe's history. Such evidence supports the idea of primordial magnetogenesis, meaning that magnetic fields may have been created very early in the universe's history. If true, this would not only explain the magnetic fields inside galaxies today, but could also change how scientists estimate the timing of recombination, the era when the first atoms formed after the Big Bang. Voids may also help explain unusual cold spots seen in the cosmic microwave background. For example, the Wilkinson Microwave Anisotropy Probe, or WMAP, discovered a large cold spot that might be explained by a gigantic void with a radius of about 120 megaparsecs. When the Sachs-Wolf effect, which describes how gravity can alter cosmic background radiation, is taken into account, the presence of such a void could provide a natural explanation for these mysterious anomalies. Although dark energy is the leading explanation for the accelerating expansion of the universe, some scientists once suggested an alternative, that our own galaxy might be inside a very large cosmic void that is not as underdense as most others. If true, this could give the illusion of acceleration without the need for dark energy. However, as more data has been collected, this idea has become less likely, though it has not been completely ruled out. Another reason voids are valuable is because they allow scientists to test the limits of Einstein's theory of general relativity. By studying both the abundance of voids and the abundance of galaxy clusters together, researchers can look for deviations from general relativity in low-density environments on very large scales. Inside voids, scientists often notice that the conditions or cosmological parameters do not exactly match those found in the rest of the universe. This difference makes voids excellent places to study how galaxies grow and cluster when the background conditions are slightly different. Larger voids often remain in what scientists call the linear regime, meaning that most of their structures maintain simple, nearly spherical shapes. Because these regions are so underdense, the usual gravitational tug-of-war between particles is almost absent, allowing scientists to model them with very high accuracy. The parameters that tend to differ in voids include the matter density, the dark energy density, and the Hubble constant, all of which define how the universe expands and evolves. For thousands of years, scientists have looked at tiny points of light scattered across the darkness. Our early knowledge of the universe was limited to what we could see without tools, just stars shining above us. But everything began to change when the first telescopes were made. Suddenly, new worlds and fainter stars appeared. Over time, we learned that our home, the Milky Way galaxy, was just one of many. The universe, once thought to be small and simple, kept growing bigger in our minds. By the middle of the 20th century, astronomers had begun to understand just how huge the universe really is. They thought it was filled with galaxies more or less evenly spread throughout space, like dots sprinkled across a huge sheet. It was a tidy and simple picture, one that made sense at the time, but then something surprising happened. A discovery came along that completely changed that picture. It showed that the universe wasn't evenly filled with galaxies after all. In fact, it revealed that there were giant patches of space, huge holes, where galaxies were almost completely missing. This discovery opened a whole new part in our knowledge of how the universe is built. And at the center of that finding was the discovery of a cosmic giant, the Bootes void. This amazing discovery was made in the early years of the 1980s by a group of astronomers led by Robert Kirshner. His team included August Oehmler Jr., Paul Schechter, and Stephen Schechtman. Together, they were working on a big project to study how galaxies are spread out across space. But this wasn't just a matter of looking through a telescope and counting stars. To really map the universe, they needed to figure out not only where galaxies appeared in the sky, but also how far away they were from Earth. This extra detail, distance, would help them make a kind of three-dimensional map, showing how galaxies gather, stretch into long threads, and leave behind huge empty areas. To do this, they used a powerful method called redshift. Redshift works a bit like how sound changes when a police siren moves away from you. The sound gets lower because the waves are stretched out. With light, something similar happens. When a galaxy moves away from us, the light it gives off is stretched out, shifting toward the red part of the rainbow of colors. The more stretched it is, the faster the galaxy is moving away, and the farther away it must be. This idea goes back to the early 20th century, when the astronomer Edwin Hubble found that nearly every galaxy is moving away from us. He also found that galaxies farther away move faster. This link between speed and distance, now called Hubble's law, lets scientists figure out how far a galaxy is just by measuring its redshift. So, using redshift, Kirshner and his team looked at thousands of galaxies. They pointed their telescopes at a certain part of the sky and gathered the faint light coming from very far away galaxies. Then they split this light into a rainbow of colours, called a spectrum, to look for special patterns. These patterns, like a fingerprint, told them what elements were in each galaxy and, more importantly, how much the light had been stretched. With this information, they worked out how far each galaxy was. As they collected more and more data, they slowly built up a detailed three-dimensional picture of where galaxies were in that part of the universe. But as they kept mapping the galaxies, they saw something strange. In one part of the sky, specifically in the direction of the constellation Bootes, there were almost no galaxies at all. This wasn't because their tools failed or because the region was blocked by dust. Their telescopes were working fine, and they were still seeing galaxies nearby and far beyond that area. But right in the middle, there was a giant stretch of space that was shockingly empty. It looked like a huge bubble in the cosmos, a round zone hundreds of millions of light years across with almost nothing inside. This discovery, first noticed in the year 1981, wasn't something they announced right away. Science takes time. They had to be sure that the void was real. They had to rule out other options like mistakes in their tools or faint galaxies being missed. So, over the next few years, they checked everything again. They used different telescopes, took more measurements, and did careful calculations to make sure the empty region wasn't just an error. By the year 1987, after years of hard work and careful study, they formally shared their findings in a major science paper. They named this huge empty space the Bootes Void, after the constellation in whose direction it lies. The Bootes Void turned out to be one of the largest cosmic structures ever found. Early guesses showed that it was about 250 million light-years across. To understand just how big that is, consider this. Our whole Milky Way galaxy is only about 100,000 light-years across. That means you could fit thousands of Milky Way-sized galaxies inside the Bootes Void, and yet this entire region holds only a few of them. The discovery was a turning point. It showed that the universe is not just filled with stars and galaxies scattered like sugar in tea. Instead, the universe is full of shape. Thick clusters and long threads of galaxies that surround vast, empty regions like the Bootes Void. This made scientists think about the universe in a new way. Rather than being the same everywhere, the cosmos seems to be shaped like a giant web. Galaxies are strung along lines, and these lines twist and turn through giant bubbles of nothingness. This is what scientists now call the cosmic web. The Bootes Void, one of its most striking parts, helped reveal this hidden structure of the universe. It showed that even in the vastness of space there are patterns, strange, beautiful, and sometimes haunting, in the way matter is spread. The science world reacted with a mix of amazement and excitement when the Bootes Void was discovered. It wasn't just the size of the void that shocked researchers, it was what it meant for our knowledge of the universe. Before this, many of the simpler models of the cosmos had assumed that matter was spread out more or less evenly, like butter on bread. But this discovery changed everything. Here was a giant region of space, stretching hundreds of millions of light-years across, that was almost completely empty. That kind of emptiness didn't fit the tidy, balanced picture many scientists had in mind. This surprising finding sparked a wave of new research. Scientists began to take a closer look at the first moments of the universe, trying to figure out how such a giant, empty region could have formed. Questions about the roles of dark matter and dark energy, those unseen forces that shape the structure and fate of the universe, became even more important. Researchers wanted to know if these mysterious pieces could help explain why some parts of the universe are filled with clusters of galaxies, while others, like the Bootes Void, are strangely silent. The discovery also showed how powerful and useful large redshift surveys could be. Before this, most astronomers had focused their attention on single galaxies or small groups of them. But the Bootes Void made it clear that to really understand the universe's shape, scientists needed to map far bigger parts of space. It was a change in thinking. The universe wasn't just a scattered group of stars and galaxies. It was a vast connected system, full of patterns, areas of great thickness, and areas of near total emptiness. In the years after the discovery, astronomers kept scanning the skies with better tools and more advanced redshift surveys. These later studies confirmed that the Bootes void was very real. They also found other similar voids, some smaller, but still very big. Surprisingly, scientists even spotted a few lonely galaxies inside the Bootes void. These rare galaxies were not completely cut off, but floated like tiny islands in a cosmic sea. Their loneliness makes them very valuable to scientists, because they offer a rare chance to study how galaxies grow on their own, far from the usual pulling and tugging found in crowded areas of space. The methods and tools created during the study of the Bootes void have since become vital in the effort to map the universe. Thanks to this breakthrough, scientists have found countless other structures, some packed with galaxies, others almost totally empty. The Bootes void became more than just a strange dark patch in the sky. It became a sign of scientific progress, a reminder of how much we still don't know, and how much the universe can surprise us when we dare to look deeper. Its discovery in the early years of the 1980s did not just reveal a hole in space. It revealed a hidden part of the universe's design, something far more complex and puzzling than anyone had guessed. It showed us that the cosmos is not evenly filled, but shaped by both bright bursts of matter and giant whispering voids. The universe is unimaginably huge, a place so big that the usual ways we measure distance, like kilometers or miles, quickly become useless. In our daily lives, we think in terms of distances we can walk, drive, or fly. But in the grand scale of the cosmos, such units are far too small to make sense. When scientists talk about galaxies, or even more massive structures made of many galaxies, they need something much bigger. That's where the light year comes in. A light year is the distance that light, which moves faster than anything else we know, can travel in one Earth year. Light moves at a breathtaking speed of about 300,000 kilometers every second. Over the course of a year, that adds up to about 9,460 billion kilometers. Just imagine that. A single light year equals nearly 10 trillion kilometers. We need this giant unit because the universe is so large that even something as fast as light takes a long time to get from one place to another. But even with light years, the numbers involved in describing the cosmos quickly grow so large they seem almost impossible to picture. Our minds are built to understand a trip across town, a road across a country, or maybe even a flight across the globe. But how do we picture a journey that would take light millions of years? This brings us to one of the most amazing features ever found in the universe, the Bootes void. This isn't just a big gap in space, it's a huge hole in the structure of the universe, a place so empty and so wide that it pushes the limits of human imagination. When astronomers first mapped it out, they guessed it to be about 250 million light-years wide. Pause and let that number sink in. 250 million years is how long it would take light to cross from one side of the void to the other. To give some background, Earth itself is only about 4,500 million years old. That means light has to travel for more than 5% of Earth's whole lifetime just to get across the Bootes void. That alone gives you an idea of how big this space is, not just large, but truly massive, even by space standards. And keep in mind, this isn't just a flat gap like a hole in a sheet of paper, it's a three-dimensional ball, an almost perfectly round bubble of nothingness inside the universe. To see just how huge this void is, let's compare it to something we know a little better, our home galaxy, the Milky Way. The Milky Way is a beautiful spiral galaxy filled with between 100 billion and 400 billion stars, not to mention giant clouds of gas and dust, and a supermassive black hole sitting quietly at its center. From one end to the other, the Milky Way stretches about 100,000 light-years. Now, if the Bootes void is 250 million light-years wide, and the Milky Way is 100,000 light-years across, then it would take 2,500 Milky Ways lined up end to end just to span the width of the Bootes void. Picture that, 2,500 galaxies, each filled with billions of stars, all arranged in a line just across this one giant emptiness. That picture makes the sheer emptiness of the Bootes void even more shocking. If you place the entire Milky Way galaxy right in the center of it, our whole space neighborhood would be nothing more than a tiny dot, swallowed by a sea of darkness. From the edge of such a lonely Milky Way in the middle of the void, if you looked out into space, the night sky would look heartbreakingly empty. You wouldn't see the familiar arch of stars that make up our galaxy. You might not even see any nearby galaxies at all. The closest galaxy could be hundreds of millions of light years away, so far that it might appear as just the faintest, ghostly blur, if it were visible at all, even through the most powerful telescope. In such a place, the sense of cosmic loneliness would be crushing. There would be no nearby galactic neighbours, no gravitational dances between galaxies, no blasts of supernovae from nearby stars lighting up the skies. Just cold, silent darkness. The Bootes void would live up to its name perfectly. It would truly be a void, a vast and nearly perfect example of cosmic loneliness. The gaps between galaxies in this region are not just a little bigger than usual, they're so wide that the normal idea of galactic neighbourhood simply doesn't fit anymore. This isn't a slightly empty region, it's a place that has been cleared of galaxies over billions of years. Let's step back even further and think about a larger view of our space surroundings. The Milky Way isn't alone. It belongs to a family of galaxies called the Local Group. This small cluster includes our Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and about 50 dwarf galaxies, all held together by gravity. From one side to the other, the Local Group stretches about 10 million light-years. That sounds like a lot, but again, it's tiny compared to the Bootes void. If you tried to stretch local groups across the width of the Bootes void, you could fit about 25 of them in a row. This tells us that the Bootes void is not just empty when compared to a single galaxy, it's empty even when compared to groups of galaxies. In the Local Group, galaxies interact with each other, pulling and twisting through gravity, forming stars and sparking bursts of activity. But inside the Bootes void, such interactions are almost missing, simply because there are so few galaxies around. This is the true size of cosmic emptiness. It's not just that there's less stuff in the Bootes void, it's that the entire setup of galaxies and clusters that make up the universe seems to have skipped over this region. Whatever processes shape the large-scale structure of the universe left this particular area shockingly blank. The Bootes void stands as a sign of the enormous, mysterious, and sometimes lonely nature of the universe. A vast, unseen gulf hidden behind the glittering spread of stars that we see when we look up at the night sky. To truly understand just how gigantic the Bootes void is, we can compare it to other giant structures in the universe. Structures made up of galaxies grouped together, like galaxy clusters, and even bigger ones called superclusters. A galaxy cluster is like a space city, packed with hundreds or even thousands of galaxies. All of these galaxies are tied together by gravity, forming a dense and heavy structure. These clusters can stretch across distances from around 3 million to 30 million light-years. One well-known example is the Virgo cluster, which lies fairly close to us in space terms. The Virgo cluster stretches about 10 million light-years across, and our own local group of galaxies is slowly moving in its direction. Now, here's the amazing part. Even a galaxy cluster as big as the Virgo cluster would look tiny when placed inside the Bootes void. You could line up 10, 50, or even 100 of these giant clusters side by side, and still not completely fill the width of the Bootes void. The difference in density is striking. A galaxy cluster is like a busy, crowded city, while the Bootes void is like an endless desert with almost nothing in sight. But the universe doesn't stop at galaxy clusters. It builds even larger groups called superclusters. A supercluster is an enormous web of galaxy clusters and smaller galaxy groups, all loosely tied together by gravity. These are the largest known structures in the universe, forming vast filaments and space highways of galaxies that can stretch for hundreds of millions of light-years. One such structure is the Laniakea supercluster, which includes our own Milky Way galaxy. Laniakea stretches about 500 million light-years, an unimaginably vast distance. Now, the Bootes void has a width of about 250 million light-years, which is about half the size of Laniakea, but still bigger than many other well-known superclusters. This means that the Bootes void isn't just bigger than single galaxies or small galaxy groups, it is bigger than some of the grandest galaxy structures in the whole universe. This fact alone makes the Bootes void stand out as something truly special. It's not just an empty gap between galaxies, it's a vast space absence that matches the size of the universe's largest and most complex structures. The universe is not evenly filled with galaxies like raisins in a cake. Instead, it is more like a sponge, with thick galaxy-rich areas separated by enormous empty bubbles. The Bootes void is one of the biggest of those bubbles, and here's where things get even more amazing. The Bootes void isn't just wide, It's a three-dimensional ball, like a bubble floating in space. That means it has volume, not just area. To understand how empty this bubble truly is, let's think in terms of volume. The size of a sphere is determined by the cube of its radius, which means that even a small increase in radius makes a sphere's volume grow enormously. The Bootes void, one of the largest empty regions ever found in the universe, has a radius of about 125 million light-years. To understand how massive that is, let us compare it to our own Milky Way galaxy. The Milky Way has a radius of about 50,000 light-years and is not a sphere at all. It is more like a flat disk with long spiral arms. But just to make the comparison simple, imagine the Milky Way as a perfect sphere. Even then, the Bootes void would be billions of times larger in volume. To put it another way, if you could fit the Milky Way inside the Bootes void, you would need billions of Milky Way-sized spheres just to fill the same space. It is a difference as great as comparing a single grain of sand to an entire mountain range. And the strangest part is this. The Bootes void is not filled with billions of galaxies, it is nearly empty. A cosmic void is not just a gap where galaxies are thinly spread, it is a whole region of the universe where galaxies are missing almost entirely, leaving behind an enormous bubble of emptiness. Now imagine what it would mean to cross this vast hollow. Suppose we had a spaceship that could travel at 1/10 the speed of light, a speed far beyond anything humanity can currently build. Even at that incredible pace, the trip from one end of the Bootes void to the other would take more than 2.5 billion years. For comparison, life on Earth has existed for about 3.5 billion years, so a single journey across the void would last almost as long as the entire history of life on our planet. In reality, our fastest spacecraft, like the Voyager probes launched in the late 20th century, move at only a few tens of kilometers per second. At such a slow pace compared to the vastness of space, crossing the Bootes void would take far longer than the current age of the universe itself, which scientists estimate to be around 13.8 billion years. That means the idea of travelling across the void is so far out of reach that it cannot even be properly imagined. Even sending a signal across this space would be unbelievably hard. Light, which is the fastest thing in the universe and the ultimate speed limit, would still need hundreds of millions of years to cross the Bootes void. If a civilization were inside the void and tried to send a message to another galaxy, that message would take longer to arrive than the entire span of human civilization on Earth. If anyone were to live inside the Bootes void, though this is purely a thought experiment since such a region is unlikely to support life, they would find themselves in near total isolation. The nearest galaxies would lie tens of millions of light years away. The night sky might show nothing but faint, ancient starlight that has travelled for hundreds of millions of years just to reach them. The loneliness of such a place would be beyond anything we can picture. Still, when astronomers call the Bootes void a void or an empty space, they do not mean it is completely blank like a perfect vacuum. In astronomy, empty simply means that there is much less matter there than elsewhere in the universe. Even in the very heart of the Bootes void, there are still a few scattered hydrogen atoms floating around, the occasional photon of light left over from the Big Bang in the form of the cosmic microwave background, and of course the unseen but ever-present dark matter, which we know must exist even though we cannot see it directly. On average, the universe usually has a few atoms of matter in every cubic meter of space. The Bootes void, however, may have less than a single atom in each cubic meter, possibly far less. That makes it one of the most underfilled regions of space ever discovered, and yet, even this great emptiness is not fully deserted. Astronomers have detected around 60 lonely galaxies drifting inside the Bootes void. These galaxies are spread apart by distances of tens of millions of light years. In any other part of the universe, such gaps would be seen as enormous, but inside the Bootes void, such separation is simply the normal condition. This remarkable emptiness is not just a strange curiosity. It teaches us something vital about how the universe is built. The cosmos is not evenly spread out. It is not smooth like milk in a glass. Instead, it is clumpy, uneven, and filled with contrasts, regions where galaxies gather together in bright webs of light, and vast silent regions where there is almost nothing at all. The Bootes void is one of the grandest examples of these silent regions, and by studying it, astronomers are forced to widen their understanding of the universe. They see that the cosmos is not only made of stars, galaxies, and brilliant lights, but also of silence, emptiness, and an unimaginable darkness that stretches across billions of light years. To understand where the Bootes void is located in the vastness of the universe, we need to think about something called cosmic geography, the way the universe is arranged on a very large scale. Just like Earth has its own shape with continents, oceans, mountains, and valleys, the universe also has a kind of structure, only on an unimaginably larger scale. The stars and galaxies are not just spread randomly in all directions. Instead, they form a huge connected pattern, often called the cosmic web. This cosmic web is made up of giant, delicate strands, which scientists call filaments. These filaments are filled with galaxies like beads on a thread, stretching for hundreds of millions of light years. Where many filaments meet, they form massive crossings or nodes, where galaxies bunch together in thick groups. But between these threads and crossings lie vast, dark, and empty areas. These huge spaces are called cosmic voids, and they are like the valleys of the universe, giant areas where there are very few galaxies, stars, or even much matter at all. One of the biggest and most well-known of these empty areas is the Bootes void. It is a massive, almost empty bubble in the cosmic web, and understanding where it is means first understanding where we are. Let's begin our cosmic trip right here, on Earth. Earth is one of 8 planets that circle around the Sun, which is a middle-aged star. But our Sun is not alone. It is just one of hundreds of billions of stars that make up our Milky Way galaxy. The Milky Way is a beautiful spiral-shaped collection of stars, dust, and gas that stretches about 100,000 light years from one end to the other. Our Sun is located about 27,000 light years from the center of this spiral, tucked into one of its spiral arms. But the Milky Way itself is not alone either. It is part of a small group of galaxies called the Local Group. This group includes the Milky Way, our closest large neighbor, the Andromeda Galaxy, and about 50 smaller dwarf galaxies. The Local Group covers a region about 10 million light-years across. Now, the Local Group is being slowly pulled toward a much bigger gathering of galaxies called the Virgo Cluster, which is about 55 million light-years away from us. And both the Local Group and the Virgo Cluster belong to a much larger region of space called the Laniakea supercluster. This supercluster is a huge gravity-connected region of the universe that stretches roughly 500 million light-years. It's like our cosmic continent, a vast area filled with galaxies, clusters, and filaments, all held together by gravity. So, our full cosmic address would be Earth, Solar System, Milky Way, Local Group, Virgo Cluster, Laniakea supercluster. Once we understand where we are in the universe, we can then look out into the distance to find the Bootes void. From our point of view on Earth, it appears in the direction of a star pattern called Bootes, also known as the herdsman. Now, star patterns are just shapes of stars that look like they are grouped together in the night sky, but in reality these stars can be very far apart in 3-dimensional space. So when we say that the Bootes void is in the direction of Bootes, we mean that if you point a telescope toward that area of the sky, and then measure how far away the galaxies are, you'll come across a huge and surprising emptiness, a gigantic 3-dimensional round region where almost nothing exists. It's not just a dark patch of sky, but a massive bubble-like hole in the structure of the universe. The center of the Bootes void is thought to be about 700 million light-years away from Earth. That means the light coming from its center began traveling toward us 700 million years ago, a time when life on Earth was still mostly in the ocean and complex creatures were just starting to appear. So when we look at the Bootes void, we're not only looking far away in space but also far back in time. This giant quiet area stands as one of the most mysterious and interesting features in the grand layout of the universe. The Bootes void is not something we can find just beyond the edges of our galaxy. In fact, it lies unimaginably far away, far beyond our local galactic neighborhood, even beyond the edges of our massive home supercluster known as Laniakea. To reach even the closest edge of the Bootes void, one would have to travel several hundred million light-years through space. That makes it an incredibly far feature in the wide layout of the universe. If we could spread out a gigantic map of the universe with Earth roughly at the center, the Bootes void would appear as a huge, dark, empty bubble, located far away from us. Far beyond not just the Milky Way galaxy, but even beyond the entire supercluster we belong to. It is a structure of the far universe, not something nearby or local. The Bootes void is a perfect example of what scientists call a cosmic void. These voids are enormous, empty areas that help shape the large-scale layout of the universe. To picture this layout, imagine a giant sponge or a web of soap bubbles. The parts of the universe that glow with stars and galaxies, the galaxy clusters and superclusters, gather along the outer layers of these bubbles. These glowing threads and walls are called filaments, and they're where matter is clumped together over billions of years, pulled in by gravity. But the spaces in between, the hollow parts of the sponge, are the voids. These are vast stretches of space where very few galaxies exist. The Bootes void is one of the biggest and clearest of these empty areas. Imagine for a moment a vast road system in space. The filaments are like busy cosmic highways packed with the movement of galaxies racing along them. Now imagine a massive abandoned roundabout or empty plaza in the middle of these roads. That's the Bootes void. It's like a forgotten district in the heart of the universe, a place where very little happens, but which still plays an important role in the overall design. The Bootes void shows us that matter in the universe is not spread out evenly, but instead arranged into a detailed, foamy design. All around the Bootes void, astronomers have seen some of the universe's largest structures. While the void itself is strangely empty, it is surrounded by thicker regions of the cosmic web, like a hollow in a sponge surrounded by thick walls. For example, parts of the Hercules supercluster and the Corona Borealis supercluster are located nearby, though still hundreds of millions of light-years away. These mighty gatherings of galaxies act like the rocky shores that mark the edges of a cosmic ocean. And that's exactly what the Bootes void is, a gigantic ocean of emptiness, separating the continent-sized superclusters of galaxies. Over the course of billions of years, the pull of gravity from the great chains of galaxies and clusters that surround the Bootes void has slowly drawn matter away from it. Little by little, this has left the Bootes void even emptier than before. And as the universe itself continues to expand, the process does not stop. It keeps stretching this great hollow, making it grow larger and more striking with time. This means the Bootes void is not just an accidental gap in the universe, it plays a role in the very way the cosmos is built, marking out the huge open regions that lie between the crowded neighborhoods of galaxies. To picture this more clearly, it helps to compare it to something on Earth. Imagine looking at a map of our planet. The continents are like the galaxy-filled regions of space, full of land, people and activity. The wide oceans, by contrast, are mostly empty of land, and they resemble the great cosmic voids. The Bootes void is like one of the largest oceans on this cosmic Earth, a vast basin of emptiness lying between the galaxy continents. Just as a ship crossing the middle of the Pacific Ocean may travel for days without seeing a single island, a galaxy drifting through the heart of the Bootes void would find itself surrounded by darkness, with no companions nearby. This picture helps us realize that the Bootes void is not a meaningless gap, but a natural part of the universe's overall pattern. Astronomers have found many other cosmic voids, ranging in size from about 10 million light-years across to several hundred million light-years. But among them all, the Bootes void stands out. It was one of the very first truly massive voids ever discovered, and when scientists first measured its vast size, they were stunned. That discovery made it a classic example, a kind of reference point used to better understand other voids. While it is not the only one of its kind, it remains famous because of its size, its clear boundaries, and the way it dramatically showed that some regions of the universe can be almost completely empty. The Bootes void also sits in a place that is very typical for voids of its size. Around its edges are glowing filaments made up of countless galaxies, along with brilliant clusters of stars and gas. Together, these form the scaffolding of the universe, the great cosmic web that holds everything in place. By studying how the Bootes void fits into this vast pattern, astronomers can test their ideas about how the universe has grown and changed. For example, by looking at how galaxies are spread around the edges of the void and how the void itself has stretched and expanded over time, scientists can learn more about a mysterious force called dark energy. This strange, unseen energy seems to be pushing space apart, helping to make these empty areas even larger. So the Bootes void is far more than just a blank patch of space. Its position, its immense size, and its relationship with the surrounding galaxies make it a key feature in the grand design of the cosmos. To astronomers, it acts almost like a witness, silent yet powerful, showing how the universe has been shaped by both matter and emptiness, by light and darkness, across billions of years. The universe we see today is filled with an amazing variety of shapes and structures. From the tiniest pieces of matter, atoms, to gigantic groups of galaxies stretching across millions of light years, everything is arranged in patterns that are both beautiful and complicated. But the universe didn't always look this way. If we go back in time to the very beginning, right after the Big Bang, more than 13 billion years ago, we find a universe that was shockingly different. It was unimaginably hot, extremely thick, and, most importantly, almost perfectly smooth. Picture a huge pot of perfectly mixed cosmic soup, with matter and energy blended so evenly that no part was different from another. There were no stars, no galaxies, no groups of galaxies, no empty gaps. Just a glowing fog of tiny particles and light, spread out almost the same everywhere. Yet today, when we look into space, we see a universe filled with shining galaxies gathered into long twisting threads, while between them lie vast dark voids, huge empty regions like the famous Bootes void, which stretches across hundreds of millions of light years. How did we get from that smooth, hot soup to the rich, bumpy, web-like structure we see today? This question lies at the centre of modern studies of the universe. The answer, as surprising as it may sound, begins with unimaginably tiny differences that existed right from the start. Differences so small they were almost invisible. But they were enough. Over billions of years, with the help of gravity and the steady stretching of space, these tiny differences grew into the huge cosmic structures of today. The great empty voids, including the Bootes void, are not just random gaps. They are natural results of this long cosmic story. Let's begin this story at the very first moments, when the universe was still younger than a fraction of a second. Although the early universe was almost completely smooth, it wasn't perfectly so. Thanks to quantum physics, the science that describes the strange behaviour of things at the smaller scales, we know that there must have been tiny bumps and dips in the spread of matter and energy, even in this smooth soup. These small wiggles in density and temperature, far too small to notice with the naked eye, were like soft ripples on a calm pond. These ripples weren't made by chance. Scientists believe they came from quantum events that took place when the universe was smaller than a single atom. Then came an event called cosmic inflation, a sudden, dramatic swelling that happened in less than a trillionth of a second. This swelling stretched those tiny ripples across the universe, turning them into the seeds from which everything else would grow. In some places, there was just a little more matter than average. In others, there was a little less. And from these almost invisible differences, the structure of the entire universe began to take shape. The force that began shaping the universe using those tiny differences was gravity, the invisible pull that draws things with mass together. Even though the differences in density were very small, gravity started working on them right away. In areas with a bit more matter, gravity's pull was slightly stronger, and it began pulling in even more matter from nearby regions. These denser spots grew heavier and more crowded over time. Meanwhile, areas with a bit less matter felt weaker gravity. As nearby matter was pulled away toward denser regions, the less crowded spots became even emptier. It's a bit like a snowball effect, but with matter being unevenly gathered. The rich, in terms of matter, got richer, while the poor got poorer. Gravity acted like a cosmic vacuum cleaner, sucking material away from the thin areas and piling it up in the regions that already had more. Slowly, over billions of years, this process made the dense regions denser and the empty ones emptier, forming groups of galaxies on one side and vast empty voids on the other. This process has a name: gravitational instability. It's a key idea in understanding how the universe's structures grow. You can think of it like a fragile house of cards. A small shake, a little tremor, is all it takes to start a collapse. In the case of the universe, those small tremors were the early differences in density. Over time, gravity made them bigger. Regions with more matter began to collapse inward, pulling in gas and the strange substance known as dark matter. These became the glowing threads and knots of the cosmic web, the filaments of galaxies and giant groups we see scattered throughout the universe today. At the same time, the less dense areas began to spread out faster than the rest of the universe. As gravity pulled material away from them toward the growing dense regions, they lost more and more of their contents. These regions, drained by the gravitational hunger of their neighbours, became the cosmic voids. They are not just leftover spaces, they are vital parts of how the universe organized itself. The entire layout of the universe came from this simple but powerful process of gravity sorting matter into crowded and empty zones. But there's another major player in this grand story, one we cannot see directly. It's called dark matter. Unlike normal matter, dark matter doesn't shine, reflect, or block light. It doesn't react with light or magnetism, which means telescopes can't detect it the way they do stars or gas clouds. But we know dark matter is there because of the way its gravity controls the motion of galaxies and the shape of space itself. Scientists think that dark matter makes up about 85% of all the matter in the universe. That means for every bit of normal matter, like the stuff that makes you, the Earth, the stars, and everything we can see, there's more than 5 times as much dark matter. In the early universe, it was these slightly denser patches of dark matter that first began to clump together. Their gravity pulled in even more dark matter and then attracted normal matter as well. These early clumps acted like invisible frameworks, skeletons on which galaxies and groups could form and grow. And just as dark matter helped build the dense parts of the universe, it also shaped the empty ones. Areas with less dark matter ended up becoming the voids. Although these voids still contain some dark matter, they have much less of it than the thicker filaments and groups. The presence, or lack, of dark matter played a central role in deciding where galaxies would form and where empty spaces would be left behind. In this way, dark matter quietly set the stage for the grand cosmic play, deciding where light would shine and where darkness would stay. So, the vast emptiness of the Boots void, and others like it, is not a cosmic accident. It is the natural result of billions of years of tiny differences growing under the pull of gravity, guided by the invisible hand of dark matter and shaped by the stretching of space itself. From the smallest ripples in a sea of fire, the universe built everything: bright galaxies, majestic groups, and the dark, silent spaces in between. Besides the pull of gravity, there is another powerful force that plays a major role in shaping the empty spaces of the universe. This force is the ongoing stretching of the universe itself. The universe is not still or frozen in place. Ever since the Big Bang, which happened more than 13 billion years ago, space has been stretching outward in all directions. This means that the distance between galaxies is steadily increasing, and the universe keeps getting bigger with time. This cosmic stretching plays 2 different roles depending on the size you're looking at. On smaller scales, like inside galaxies or within galaxy groups, gravity is strong enough to hold things together. Even as space stretches, gravity keeps stars, gas, and dark matter clumped into these thick regions. But on much larger scales, such as the vast stretches between galaxy groups, the stretching of space becomes the stronger force. And here's where the story of the great voids truly begins. In the very first moments after the birth of the universe, not every place was the same. Some regions had just a little less matter than others, like patches that were slightly thinner or lighter. These thinner areas would later grow into what we now call cosmic voids. As the universe began to stretch and expand, these underfilled regions spread out even faster than the areas that contained more matter. The small amount of material inside them, tiny particles, gas, and even whole galaxies, was slowly pulled farther and farther apart. With time, these places grew emptier and emptier. This steady thinning of matter, caused by the stretching of space itself, is known as cosmic dilution. You can imagine it by picturing a balloon with tiny dots drawn across its surface. At first, the dots are close enough together, but as you blow air into the balloon, the surface grows, and the dots drift farther apart. If some dots were already farther apart at the start, they will end up becoming even more widely separated as the balloon continues to inflate. That is almost exactly what happens inside cosmic voids. Space itself acts like the stretching balloon, constantly pushing the few scattered particles within the voids away from each other, making them larger and emptier as the ages roll by. These great voids are not simply blank holes floating in the universe. They are a natural outcome of the way space behaves. Their growth is deeply tied to the grand cosmic design known as the cosmic web. This web is a breathtaking network made up of enormous filaments of matter, dense clusters of galaxies, and the vast, silent voids lying between them. But this delicate, intricate structure did not appear in an instant. It took billions upon billions of years to unfold. To uncover how such a pattern came to be, scientists build powerful computer simulations, like miniature digital versions of the universe. They begin these models with the conditions believed to exist shortly after the Big Bang more than 13 billion years ago, tiny ripples in the density of matter, a blend of ordinary matter and invisible dark matter, and the unstoppable expansion of space. They then let the simulation play out over billions of years. As gravity tugs on matter and expansion stretches it outward, something extraordinary begins to form. Long glowing strands of matter called filaments, crowded regions full of galaxies called clusters, and vast empty spaces called voids. The most astonishing part is that the patterns in these digital universes look strikingly similar to what astronomers see when they scan the real night sky with their telescopes. This tells us that the rules of physics, gravity, cosmic expansion, dark matter, and dark energy are powerful enough to explain how the universe shaped itself. One of the most famous examples of such emptiness is the Bootes void. This giant hollow region is one of the loneliest places we have ever discovered in the universe. Its enormous size and incredible emptiness make it stand out. Yet, its existence is not a mistake or a puzzle. Computer models show that regions like the Bootes void arise naturally when the universe grows and evolves under the very laws of physics we already know. These simulations are far more than just fascinating digital pictures. They allow scientists to test their ideas. By adjusting the amount of dark matter or changing the strength of dark energy within their models, researchers can see how the universe would appear differently. This gives them a deeper understanding not only of what the universe looks like today, but also of why it looks this way and which laws were shaping it from the very beginning. Of course, scientists cannot rely only on computers. Observations of real cosmic voids are just as important. Astronomers carefully chart the locations of galaxies, measure their distances, and study the rare few galaxies that survive inside these quiet, lonely regions. By comparing these real measurements with their simulations, scientists can check whether their ideas are correct. When the behavior of actual voids matches what appears in the digital models, it strengthens the belief that their understanding of the universe is on solid ground. The Bootes void is especially important in this work. Its vast hollowness and incredible scale are not strange or surprising. On the contrary, they are exactly what we would expect to see if tiny ripples in the early universe, over the course of more than 13 billion years, were stretched and sculpted by the forces of gravity, dark matter, dark energy, and the unending expansion of space itself. The scale of emptiness in the universe is one of the most fascinating and puzzling things to think about. The emptiness is not just small gaps here and there between stars or galaxies, but enormous regions that stretch across distances so vast that human imagination struggles to keep up. These regions are called voids, and when we compare them to the size of galaxies, galaxy clusters, and even superclusters, we begin to realize just how staggering the scale of this emptiness truly is. Let's begin with a galaxy. Our own Milky Way galaxy is a massive collection of stars, gas, dust, and invisible dark matter, bound together by gravity. It holds hundreds of billions of stars, and yet the distances between those stars are already immense. Light, which travels at the fastest speed in the universe, takes about 100,000 years to cross from one side of the Milky Way to the other. That means if a beam of light started at one end of the galaxy, at the same time humans were first beginning to make tools out of stone millions of years ago, it would still be travelling across the galaxy even today, and would not have reached the far end yet. This is the scale of just one galaxy, and already it stretches the mind. But galaxies do not exist on their own. They are grouped together in collections called galaxy clusters. Our own Milky Way belongs to what is known as the local group, a small cluster of galaxies bound together by gravity. The local group contains more than 50 galaxies, although most of them are tiny compared to the Milky Way and the Andromeda galaxy, which are the two dominant members. The Andromeda galaxy is about the same size as the Milky Way, and it lies a little over 2.5 million light-years away from us. That means light that we see today from Andromeda began its journey before the first ancestors of humans had fully developed the ability to use language. To cross just the space between the Milky Way and Andromeda would take light longer than the entire history of humanity. And yet, this distance is considered small on the cosmic scale. When we expand beyond clusters, we find that clusters themselves are not scattered randomly, but are arranged in even larger structures called superclusters. A supercluster is a vast collection of many galaxy clusters and groups. Our local group, for example, is part of the Laniakea supercluster, which contains tens of thousands of galaxies spread over a region about 500 million light-years across. To imagine that, think of a bubble so large that if a beam of light started at one edge when dinosaurs were alive on Earth, it would still be travelling and would not have reached the other edge even today. That is the scale of a supercluster. And yet, as gigantic as galaxies, clusters and superclusters are, the voids in between them are even larger. Voids are enormous cosmic deserts where almost nothing exists, just a sprinkling of galaxies here and there, like a few grains of sand scattered across a wide empty beach. The largest voids can be hundreds of millions of light-years across. One of the most famous is called the Bootes Void. This particular void is roughly 250 million light-years wide. To put that in perspective, if our Milky Way galaxy, with its 100,000 light-year diameter, were placed next to the Bootes Void, it would look like a tiny speck beside a vast canyon. The Bootes Void could swallow thousands of galaxies like the Milky Way and still have room left over, yet it is almost entirely empty. The Bootes Void was first discovered in the early 1980s, when astronomers mapping the positions of galaxies noticed that a huge region of space seemed to be missing nearly all of them. At first, it seemed so strange that some scientists wondered whether it might be an error in the data, or whether something unknown was hiding there. But as more observations came in, it became clear that this emptiness was real. Within that massive volume of space, there are only a handful of galaxies, far fewer than anyone would expect. Imagine standing on a hill overlooking a great city and finding that instead of millions of lights, there were just a few scattered lamps glowing in the darkness. That is what the Bootes Void looks like to astronomers. Comparing the size of voids like Bootes to galaxies is almost impossible to do in a way that feels real. A galaxy, enormous as it is, becomes tiny when placed next to a void. Even clusters and superclusters, which we often think of as the ultimate scale of structure in the universe, are dwarfed by the emptiness between them. It is as though the universe is built like a cosmic sponge, with filaments of galaxies forming the thin walls, and the insides filled with great pockets of nothingness. The galaxies gather together in long chains and walls that stretch across hundreds of millions of light-years, and the voids are the dark spaces in between. To get a better sense of the difference, let's compare some numbers more carefully. The Milky Way galaxy, with its 100,000 light-year diameter, is already unimaginably huge compared to human scales. If Earth were shrunk to the size of a grain of sand, the Milky Way would be the size of a continent. But the Bootes Void, with its 250 million light-year diameter, is more than 2,000 times larger than the Milky Way. That means if you placed 2,000 galaxies as big as the Milky Way side by side, they would still not stretch across the Bootes Void. When astronomers try to visualize this, they often say that calling the Milky Way large compared to a void is like calling a single drop of water large compared to an entire ocean. Even galaxy clusters are small next to voids. The Virgo cluster, the closest large galaxy cluster to us, is about 15 million light-years across. This cluster contains thousands of galaxies, each with hundreds of billions of stars. It is an enormous structure in its own right, but when compared to a void like Bootes, it is less than 1/15 of the size. It is like comparing a small town to an entire continent. A cluster that seems massive when we think of galaxies suddenly becomes tiny when we place it against the emptiness of the universe. When we move up to the scale of superclusters, the comparison becomes more interesting. A supercluster like Laniakea is about 500 million light-years across, which is about twice the size of the Bootes Void. So, on that scale, voids and superclusters are of a similar order of magnitude. The universe seems to have arranged itself into a pattern where superclusters form the great walls and filaments, and the voids are the gaps between them. Both are equally important to the architecture of the cosmos, like the solid beams and the open spaces in a vast building. Without the voids, the walls of galaxies would not stand out, and without the walls, the voids would not exist. The scale of emptiness becomes even more astonishing when we think about the number of stars and galaxies that are missing from voids. In a region the size of the Bootes Void, if matter were distributed evenly, we would expect to see tens of thousands of galaxies. Instead, we see only a few dozen. That means more than 99% of the galaxies we would expect to be there are absent. The voids are not just large, they are almost completely barren. If a civilization lived on a planet inside one of those galaxies in the Bootes void, their night sky would look very different from ours. Where we see a rich band of stars and many bright neighbouring galaxies, they would see almost nothing, just darkness with a few lonely lights. The emptiness of voids is not absolute. They are not perfect vacuums. There is still some matter inside them, but it is so thinly spread out that it hardly counts compared to the crowded regions of galaxy clusters. A single cubic metre of space inside a void might contain only a few atoms, whereas the same volume of space inside a galaxy could contain thousands or even millions. The difference is staggering, and it shows us just how lopsided the universe is when it comes to the distribution of matter. Most of the universe is not filled with galaxies. It is filled with emptiness. When astronomers map out the universe on the larger scales, they often describe it as looking like a cosmic web. This web is made up of filaments of galaxies and galaxy clusters stretching across space, with enormous voids in between. Each filament can be hundreds of millions of light-years long, and the voids between them can be just as large. It is one of the most breathtaking discoveries of modern astronomy, because it shows that the universe is not just random but has a grand design. The galaxies are not scattered like grains of sand on a floor. They are arranged like the threads of a spider's web, leaving behind vast, empty chambers. Thinking about this scale of emptiness changes how we see our own place in the universe. Our galaxy, which once seemed so vast and almost infinite when we only knew about it, turns out to be just a small dot along a filament in one corner of the cosmic web. Our local group is just one of thousands of small gatherings of galaxies sitting on the edge of a void. The Virgo cluster is just one small knot in a vast network, and the Laniakea supercluster is just one of many superclusters spread across the visible universe. Beyond each of these structures lies more emptiness, stretching farther than we can easily imagine. The distances involved are so overwhelming that it is helpful to think in terms of time as well as space. Light is our only way of seeing the universe, and because it travels at a fixed speed, every distance in space also corresponds to a stretch of time. When we say that the Bootes void is 250 million light-years across, we are also saying that light takes 250 million years to cross it. That is longer than the time since the first dinosaurs walked on Earth. It means that if a civilization were living on one edge of the Bootes void and sent a signal of light toward the other edge, it would take longer than the entire history of mammals on Earth for that signal to arrive. That is how wide the emptiness really is. It is tempting to think of voids as just holes between galaxies, but they are much more than that. They are part of the very fabric of the universe. In the early days after the Big Bang, the universe was almost perfectly uniform. Matter was spread out evenly, with only tiny differences here and there. But those small differences grew over time. Where there was slightly more matter, gravity pulled it together, and galaxies and clusters eventually formed. Where there was slightly less matter, gravity was weaker, and those areas stretched out into emptiness. Over billions of years, the emptiness became emptier, while the crowded areas became more crowded. Voids are not accidents. They are the natural outcome of how the universe has evolved. The idea of cosmic voids has always fascinated both astronomers and ordinary people alike. At first glance, the very word void makes one imagine a place completely stripped of all things, a vast, endless stretch of space where nothing at all exists. The human mind pictures a kind of black, silent desert with no stars, no planets, no galaxies, and no light. But when astronomers point their powerful telescopes toward these regions and analyze them with careful measurements, they find that the truth is more complicated and far more interesting. Voids in the universe may be astonishingly empty compared to the rest of cosmic space, yet they are not truly nothingness. The mystery of whether these enormous gaps are completely hollow, or whether they still carry a thin, almost ghostly trace of matter such as faint galaxies, scattered stars or drifting gas, makes them one of the most thought-provoking parts of cosmic structure. When scientists first mapped the large-scale design of the universe in the late 20th century, they realized that galaxies were not spread out in a random and even way. Instead, galaxies tended to gather together in long chains, sheets, and dense knots. These patterns looked almost like foam or soap bubbles, with bright walls of galaxies surrounding wide, dark hollows in between. These hollows were named voids. The discovery shook our understanding of cosmic geography because the voids were unimaginably large. Some stretched across hundreds of millions of light-years. To put this in perspective, our own galaxy, the Milky Way, has a diameter of about 100,000 light-years. That means a single void can be thousands of times larger than our entire home galaxy. Such immensity forces us to wonder what truly fills these silent realms. If we imagine standing on a planet inside one of these voids, the night sky would look very different. Instead of seeing countless stars spread across the heavens, the sky would be eerily quiet and bare. Perhaps only a handful of galaxies would be visible, far away and faint. The darkness would be deeper than anything we can imagine from Earth, where the Milky Way's band of stars fills the sky with light. But does this darker, lonelier sky mean that nothing is there at all? Not exactly. Voids are not absolute vacuums. They do not lack all matter entirely. Instead, they are regions where matter is spread out extremely thin. Imagine taking a spoon of water and pouring it into a wide desert. The liquid does not vanish, but it becomes so diluted that it barely wets the sand. In much the same way, the little matter inside voids is stretched so far apart by the universe's expansion that it hardly has the chance to gather into large, bright galaxies. But faint matter is still present if we look closely enough. Astronomers have observed that some voids contain small dwarf galaxies. These are galaxies far tinier than the Milky Way. They may have only a few million stars instead of hundreds of billions. Some dwarf galaxies inside voids are so dim that they are difficult to detect even with modern instruments. Yet their presence is proof that the voids are not utterly blank. A few galaxies manage to survive there, isolated from their brighter cousins in the crowded cosmic walls. In a way, they are like lonely villages sitting in the middle of an endless desert, while bustling cities thrive far away along rivers and coasts. Gas too is scattered through the voids. This gas is not the thick swirling kind that forms visible nebulae within galaxies. Instead, it is an incredibly thin mist of hydrogen and helium, sometimes with traces of heavier elements. Scientists can detect this invisible gas when light from faraway quasars passes through it. The gas leaves subtle fingerprints on the light, allowing astronomers to confirm that matter is indeed spread across voids, though in the faintest and most delicate way. This thin trace of matter may not sound impressive, but it carries deep meaning. The universe was born with almost uniform matter everywhere, yet small differences in density set the stage for the cosmic web. Regions with slightly more matter became the sites where galaxies, clusters, and superclusters formed. Regions with slightly less matter stretched faster, drained away, and became voids. But less matter did not mean no matter. The leftover particles, atoms, and gases remain, just not enough to create rich structures like in other regions. This delicate balance explains why voids appear so empty, but still hide faint whispers of galaxies and gases. The Bootes void, one of the largest known voids, illustrates this mystery well. It spans nearly 300 million light-years across, yet astronomers have identified some galaxies within it. When it was first discovered, many thought it might truly be a hole in the universe. But later surveys showed that there are indeed faint galaxies sprinkled inside, though far fewer than in surrounding regions. This shows us that voids, even the largest ones, are not entirely barren. The presence of matter inside voids also raises fascinating questions about galaxy evolution. Galaxies inside voids live very different lives compared to those inside clusters. In dense regions, galaxies are constantly tugged and pulled by the gravity of neighbours, sometimes merging together, sometimes having their gas stripped away by surrounding heat and pressure. In contrast, galaxies inside voids are almost completely isolated. With so few neighbours around, they evolve slowly, like solitary creatures growing in peace without disturbance. Some astronomers believe that void galaxies can reveal what galaxies might have looked like in the early universe, before they were disturbed by crowded environments. The gas inside voids is equally intriguing. Although it is extremely thin, it still plays a role in the cosmic balance. Some theories suggest that the gas in voids may remain cool for billions of years, unlike the gas in clusters, which often heats up to millions of degrees. This cool gas could provide clues about how matter behaves when it is not trapped in the busy hubs of the cosmic web. It may also help explain the so-called missing baryon problem, the puzzle of where much of the ordinary matter in the universe is hiding. Observations hint that a significant fraction of this missing matter may be quietly drifting inside voids, invisible but real. We might imagine voids as vast oceans of darkness, where only tiny islands of galaxies float. The water in these oceans is almost transparent and weightless, representing the thin gas and scattered atoms. The islands are the dwarf galaxies and lonely stars far apart from one another. Sailors on such an ocean would travel for ages without seeing another shore, but they would still find occasional signs of life. Another way to think about voids is to compare them with bubbles in a loaf of bread. When dough rises, air pockets form inside, creating empty spaces. The bread itself represents the dense regions of the universe filled with galaxies. The bubbles, however, are not entirely empty. They may still carry traces of moisture and air. In the same way, voids carry traces of matter, even if they look like nothing at all from a distance. Gravity does not only pull matter together, it also creates patterns by leaving behind the underdense spaces. As matter falls into dense clusters, it drains from voids, making them appear even emptier. But the leftover matter in voids is not lost, it is simply stretched thin. Over billions of years, this process creates the striking contrast between glowing galaxy clusters and vast dark voids. It is remarkable to think that even in the emptiest regions of the universe, matter clings on stubbornly. Atoms float through endless darkness. Small galaxies shine faintly against the backdrop of nothingness. Wisps of hydrogen drift like ghostly smoke across cosmic distances. These traces prove that there is no such thing as a perfect void. The universe, it seems, never allows complete nothingness. Even its most desolate places carry subtle signs of existence. Some scientists argue that studying these faint traces is just as important as studying rich galaxy clusters. In dense regions, matter is shaped by constant interactions, collisions, and violence. But in voids, matter is left almost untouched. By observing it, astronomers can learn about the earliest conditions of the universe, when matter was more evenly spread. The thin gases and faint galaxies may hold ancient clues, frozen in time by their quiet environments. The search for matter inside voids is ongoing. Each new telescope, from ground-based surveys to space observatories like the Hubble Space Telescope and the James Webb Space Telescope, adds to our understanding. The challenge is always the same: detecting the almost invisible. Astronomers often rely on clever tricks, such as analysing the light of distant quasars, which act like flashlights shining through the voids. Every faint absorption pattern in the quasar light reveals hidden gas in the void. Even the future of voids stirs curiosity. As the universe continues to expand, galaxies will drift farther apart. Voids will grow even larger and emptier. The few galaxies inside them will become lonelier still, and the thin gas will stretch thinner. In the distant future, voids may dominate the universe even more strongly than they do today, swallowing up the spaces between the last surviving clusters. Yet even then, faint traces of matter will remain, resisting the idea of total emptiness. When we reflect on the question, are voids truly empty, we must answer with wonder rather than certainty. They are astonishingly empty compared to any other part of the cosmos, yet they still carry whispers of existence. The idea of the cosmic web begins with something very simple. When the universe was young, just after the great explosion that we call the Big Bang, everything was more or less evenly spread out. The early universe was like a hot fog of tiny particles, mostly hydrogen and helium, stretching in all directions. But it was not perfectly smooth. There were places with slightly more matter, and places with slightly less. Those small differences, smaller than a single part in 100,000, grew over billions of years into the enormous differences we see today. Where there was just a little more matter, gravity pulled even more material in, until galaxies and clusters of galaxies formed. Where there was slightly less matter, the pull of gravity was weaker, and those regions became emptier and emptier with time, expanding into the black spaces we now call voids. This tug-of-war between crowded regions and empty ones is what eventually gave rise to the cosmic web. When scientists map the universe on a grand scale, what they see is breathtaking. Galaxies are not scattered randomly like grains of sand flung across a table. Instead, they gather into long, thin chains that stretch for hundreds of millions of light years. These chains are called filaments, and they form the great highways of the cosmic web. At the places where filaments intersect, the density of matter becomes so high that enormous clusters of galaxies form, like bright knots in a net. Even larger than clusters are superclusters, sprawling systems of many galaxy clusters linked together across hundreds of millions of light years. These filaments, clusters, and superclusters form the skeleton of the universe. But between these shining structures lies the other side of the picture, immense black spaces, the voids, where few or no galaxies exist. Without these empty areas, the cosmic web would have no contrast, no definition. The dark spaces are like the silent pauses in music, making the notes stand out more clearly, or like the blank canvas between strokes of paint, giving shape to the painting. One of the most fascinating things about the cosmic web is its resemblance to patterns we see elsewhere in nature. If you look at a sponge under a microscope, you see a network of connected holes and filaments. If you look at the web of neurons in a human brain, the branching lines and nodes echo the same pattern. Even the way rivers branch and connect across a continent has similarities. This repeating structure suggests that the universe builds itself according to simple rules of physics that, when scaled up to unimaginable distances, create a pattern that seems both random and ordered at the same time. The black spaces in this pattern are not mistakes or accidents. They are a natural result of how matter and gravity interact. They show us that emptiness is not absence, but a key part of the balance. To picture the size of these structures is almost beyond imagination. A single galaxy like the Milky Way, which is home to our Sun and hundreds of billions of stars, is about 100,000 light-years across. A cluster of galaxies can be several million light-years wide. A supercluster can span hundreds of millions of light-years. And then there are voids, like the Bootes void, one of the largest known, which is about 250 million light-years across. To put that in perspective, if you were travelling at the speed of light, which is about 300,000 kilometers every second, it would still take 250 million years to cross that black space from one side to the other. The vastness of such a space defies human experience. Yet these empty places are just as much a part of the cosmic web as the glowing strands of galaxies around them. When astronomers first began mapping the distribution of galaxies in the universe, they were shocked to discover these patterns. In the 1980s, large surveys of galaxies revealed that instead of being spread evenly, galaxies formed walls, sheets, and chains that surrounded enormous empty bubbles. It was as if the universe were a frothy foam, with galaxies tracing the thin edges of bubbles and leaving the insides empty. This was the first direct evidence of the cosmic web. The black spaces that appeared between the glowing filaments were not small. They stretched across distances that dwarfed entire galaxy clusters. What was once thought of as background emptiness turned out to be one of the most important elements of cosmic architecture. The black spaces, or voids, also tell a story about time. As the universe expands, matter is constantly being pulled away from these regions and toward the denser filaments. This means that the voids are not static. They grow larger and emptier with every passing billion years. The galaxies that remain inside them are stretched apart, drifting farther and farther from each other, like tiny islands in a vast ocean. In this way, the voids act like enormous pumps, feeding the cosmic web by draining material toward the filaments. The more the universe expands, the more pronounced the web becomes, with bright highways of galaxies surrounded by ever-deepening seas of darkness. It is tempting to think of the black spaces as being utterly empty, but that is not quite true. Even inside the largest voids, there is still a thin trace of matter, very faint gas, scattered dark matter, and sometimes small, lonely galaxies that wander like lost travellers. These void galaxies are often quite different from those in clusters. They are more isolated, sometimes younger, and often show unusual shapes or properties. Because they evolve without much disturbance from neighbouring galaxies, they can provide clues to how galaxies grow in solitude. The existence of these faint traces shows that even the darkest parts of the universe are not truly nothing. They are simply regions where matter is stretched to its limits, where space dominates over substance. The cosmic web also helps scientists test their theories of the universe. According to the most accepted model of cosmology, called the lambda cold dark matter model, the universe is made mostly of invisible dark matter and mysterious dark energy. Normal matter, the kind that makes up stars, planets, and people, is only a small fraction. Dark matter is what gives the cosmic web its skeleton. Without it, galaxies would not have gathered into filaments and clusters. The black spaces reveal where dark matter is thinnest, while the filaments reveal where it is thickest. By studying the contrast between the glowing structures and the black voids, astronomers can test how well their models match reality. If the universe did not form a cosmic web with both filaments and empty regions, our theories of gravity and dark matter would need to be rewritten. One of the most striking examples of how the cosmic web looks is provided by computer simulations. Using powerful supercomputers, scientists can simulate the growth of the universe from its earliest moments to the present day. These simulations begin with tiny differences in density, just like those seen in the cosmic microwave background, the faint afterglow of the Big Bang. Over billions of years, the simulated matter clumps and stretches until it forms a web of filaments, clusters, and voids. The result is astonishingly similar to what telescopes see when they map galaxies across the sky. In both cases, the black spaces are an essential part of the picture. Without them, the web would lose its form, and the universe would look like an undifferentiated fog. It is worth pausing to imagine what it would be like to travel through this grand structure. Suppose you set out from our Milky Way galaxy and journey across the local group of galaxies to the Virgo cluster, which lies about 60 million light-years away. You would be travelling along one of the filaments of the cosmic web, a highway of galaxies stretching as far as the eye can see. Then imagine leaving that bright filament and entering one of the voids. Suddenly the galaxies would grow sparse. Instead of seeing hundreds or thousands of galaxies around you, you might see only a handful scattered across the darkness. As you travelled deeper into the void, those galaxies would drift farther apart until the space around you seemed almost completely black. After hundreds of millions of years travelling at the speed of light, you might finally reach the far edge of the void and see another filament rising out of the darkness, glowing with the light of countless galaxies. This contrast between bright highways and dark deserts is what gives the cosmic web its extraordinary beauty. The relationship between the black spaces and the glowing filaments can also be understood as a balance between push and pull. Gravity pulls matter into filaments and clusters, but the overall expansion of the universe driven by dark energy pushes space apart. In the voids, where matter is scarce, the push of expansion dominates, stretching the regions faster than average. In the filaments, the pull of gravity wins, keeping galaxies together despite the cosmic expansion. The cosmic web is therefore the visible outcome of two competing forces, gravity and expansion, interacting across billions of years. The black spaces are where expansion is most powerful, while the filaments are where gravity shows its strength. When astronomers observe the cosmic web, they often compare it to a three-dimensional spider web stretched across the sky. The filaments are the strands, the clusters are the knots, and the voids are the open spaces between. But unlike a spider's web, this one is not flat. It extends in all directions, forming a structure that fills the entire universe. If one could step outside the universe and look in from above, a thought experiment since such a view is impossible, one would see something like a glowing network floating in a sea of darkness, with bright intersections linked by long threads and surrounded by enormous black bubbles. This image, though imaginary, helps to explain how the black spaces are not separate from the web, but rather define its shape. Another remarkable fact is that the cosmic web has no clear centre. There is no special place where the filaments begin or end. The web stretches endlessly in all directions, at least as far as we can see. This means that the black spaces too are everywhere. Wherever you look in the deep sky, you find both filaments of galaxies and voids between them. The pattern repeats at scales from tens of millions to hundreds of millions of light years. It is this repeating, endless structure that gives the universe its sense of order on the larger scales. The Earth, with all its mountains, oceans and cities, is just a speck inside the Milky Way. The Milky Way itself is just one thread in a filament, and that filament is only one of countless others in the cosmic web. The black spaces between filaments are so vast that entire human civilizations could rise and fall many times over in the time it would take light itself to cross them. Yet without those empty spaces, the filaments would not exist as they do. The darkness gives meaning to the light. The sight of the universe can sometimes trick the human eye. What appears as a great black emptiness, a silent stage without stars, may not be truly empty at all. The darkness is often just an illusion, a shadow created by the limits of human vision and the limits of the instruments built to explore the skies. A person who looks into the night sky might think that the regions of blackness stretching between the bright dots of stars and galaxies are nothing more than holes in space. Yet in reality, these dark patches may still be filled with matter that cannot be seen, matter that hides itself by giving off no light. This unseen content can be gas, dust, or mysterious forms such as dark matter, which do not reflect or shine but are still part of the cosmic stage. The universe has always been far more crowded and complex than the human eye can measure at first glance. For thousands of years, people believed that the stars were fixed upon a dark curtain, spread across the sky like jewels upon velvet. The blackness behind them was thought to be absolute, a background with nothing beyond. But as science progressed, especially over the last 400 years since the first telescopes were used, it became clear that the dark spaces between stars and galaxies are not simply empty voids, but often contain structures invisible to ordinary sight. The black colour comes from a simple fact. Human eyes evolved to see only a narrow band of light, called visible light, and most of the universe does not shine in that narrow band. The eye cannot detect radio waves, microwaves, X-rays, or gamma rays. If people could see in those hidden forms of light, the universe would no longer appear as dark as it does now. Imagine standing in a forest at night with only a weak lantern. Beyond the circle of light from the lantern, the woods seem completely black. A person might believe that there is nothing there. But of course the forest is still full of trees, rocks and animals. They are hidden only because the lantern is not powerful enough to show them. The night sky works in the same way. Human sight is the weak lantern, while the universe stretches out like an endless forest. What is unseen may be far more abundant than what is seen. Telescopes have become humanity's stronger lanterns, revealing that blackness is not the same as emptiness. For example, astronomers using radio telescopes discovered that huge clouds of hydrogen gas exist in regions that appear completely black through ordinary telescopes. These clouds do not give off visible light, but they do whisper in radio waves that sensitive instruments can pick up. When radio astronomy grew during the 20th century, it transformed the way scientists saw the universe. Suddenly, what looked like empty darkness became filled with sprawling rivers of gas, sometimes stretching for millions of light years. These invisible oceans of hydrogen act as the raw material from which galaxies are built. The illusion of darkness becomes even more interesting when dark matter is considered. Dark matter makes up most of the matter in the universe, yet it cannot be seen at all. It does not shine, reflect, or absorb light in the way ordinary matter does. Instead, it reveals its presence through gravity, pulling on stars and galaxies like invisible hands. Astronomers have measured how galaxies spin and how clusters of galaxies hold together, and these motions only make sense if there is a huge amount of hidden matter, keeping them from flying apart. So even in the deepest black regions where nothing appears to shine, there may be invisible scaffolding of dark matter shaping the structure of space. The illusion is not only about matter hidden from sight, but also about distance. The farther away something is, the fainter it appears. Light from distant galaxies takes billions of years to reach Earth. Along the way, it stretches as the universe expands, turning into redder and dimmer wavelengths that human eyes cannot see. This red shifting makes galaxies fade into the darkness until they vanish from visible view. What seems like a blank area of the sky may actually contain countless galaxies whose light has stretched beyond the limits of vision. The James Webb Space Telescope and the Hubble Space Telescope have revealed that tiny dark patches of sky, when examined with deep imaging, are not empty at all. In fact, when Hubble stared at one of the darkest, most empty-looking patches of sky for many days, it uncovered thousands of galaxies packed into what had appeared to be a hole. Darkness once again proved to be only an illusion caused by the limits of sight. Another way to think of it is to picture a sea at night. Looking across the water, a person may see nothing but black waves. But beneath the surface, life teems in abundance. Fish, corals, and creatures of all shapes and sizes. The darkness does not mean the absence of life. It only hides what cannot be seen. Space works in the same way, only on a scale beyond imagination. The cosmic sea may look black, but it is alive with energy, hidden structures and particles that move unseen. There are also vast stretches of cosmic dust that play a role in the illusion of darkness. Dust grains made of carbon, silicon and ice drift between the stars. These grains block and scatter visible light, creating black patches in the sky. To the eye, such regions look like holes, but in reality, they are thick curtains hiding the stars behind them. Astronomers using infrared telescopes can peer through the dust, because infrared light can slip between the grains, revealing stars and forming galaxies that are otherwise invisible. Without infrared observations, Entire nurseries of newborn stars would remain hidden inside what appear to be dark voids. The illusion of darkness is also shaped by the way human brains process sight. The brain is tuned to contrast, bright stars against a dark background. It is natural to assume that the black areas are empty because the brain expects light to signal the presence of something. But in the universe, light is the exception, not the rule. Most of space is not shining invisible light, and much of the matter is either too cool, too thin, or too hidden to glow. Darkness is not an absence of substance, it is only an absence of detectable light. If people could ride a spacecraft into what seems like a dark void, they might quickly discover that the emptiness is more like a faint mist than a perfect vacuum. There would be atoms of hydrogen drifting at enormous distances from each other, but still present. There would be stray photons of background radiation, the afterglow of the Big Bang that fills all of space. There would be the invisible gravitational influence of dark matter, and there might even be faint traces of galaxies so far away that they can no longer be seen. The blackness is therefore not a wall of nothing, but rather a veil of invisibility. The very existence of the cosmic microwave background proves that no corner of space is truly black. This faint radiation is the leftover light from the first moments of the universe, more than 13 billion years ago. It shines everywhere, in every direction, though the human eye cannot detect it. Special instruments first discovered it in the 1960s, and since then it has been mapped in great detail. It shows that what appears to be black sky is actually glowing faintly in microwaves, a soft whisper from the beginning of time itself. To think of it another way, imagine an enormous theatre where the lights have been dimmed. The audience may believe the stage is empty because nothing is lit, but in truth, props, scenery, and actors may still be standing there in the shadows. Only when a new kind of light is shined upon them do they become visible. Telescopes that see in radio, infrared, ultraviolet, X-rays and gamma rays are like spotlights revealing different aspects of the cosmic stage. Each one shows a universe that looks less and less black, until finally the illusion of emptiness dissolves. Even the great cosmic voids, the enormous bubbles between filaments of galaxies, are not completely empty. While they appear darker than the rest of space, they still contain thin wisps of gas, a sprinkling of galaxies, and of course the invisible presence of dark matter. These voids stretch across hundreds of millions of light years, yet they are part of the structure of the universe itself. The blackness of a void is not the end of matter, but simply a thinning out, a place where light sources are rare and dim. The illusion of darkness has shaped human imagination as much as scientific discovery. Poets and thinkers once believed that the black spaces of the heavens were signs of eternity, mystery, or nothingness. Now, science reveals that those same black spaces are instead filled with hidden richness, unseen but real. The universe is not divided into places of light and places of nothing. Rather, it is all one continuous ocean, with light shining brightly in some parts and remaining unseen in others. Astronomers today continue to explore these black regions using every tool available. The discovery of dark energy, a mysterious force pushing the universe apart, came from studying the faint light of distant supernova in regions of space that looked dark at first. Particle physicists build underground detectors to catch invisible particles called neutrinos, which stream through the blackness of space by the trillions every second. The flow of time has always shaped the universe in quiet but powerful ways, and nowhere is this more striking than in the great empty regions we call voids. These enormous spaces, which seem at first like holes scattered between the shining islands of galaxies, are not fixed or frozen parts of the cosmos. They are alive with change, though their growth is not like the rapid transformations of stars exploding or galaxies colliding. Instead, voids stretch and expand slowly and steadily, moulded by the passing of billions upon billions of years. From the earliest moments after the birth of the universe, time has worked as a kind of silent sculptor, pulling matter towards certain places while leaving other places drained and hollow. Over the ages, this process has given rise to the vast cosmic web, where bright filaments of galaxies crisscross the universe and enormous dark regions lie in between them. These dark regions, the voids, have kept growing with every heartbeat of cosmic history, carrying the imprint of time itself. When the universe was first born almost 14 billion years ago, it looked nothing like the rich and complex structure we see today. In those first moments after the Great Beginning we call the Big Bang, space was hot, dense, and filled almost evenly with matter and energy. But even then, it was not perfectly smooth. Some regions had just a little more matter than others, while some had just a little less. These tiny differences, smaller than the width of a hair compared to the size of the entire cosmos, would later decide where galaxies, stars, and planets would form, and where emptiness would dominate. Time began to magnify those tiny ripples. Where there was slightly more matter, gravity slowly pulled in more, building clumps that became galaxies and clusters of galaxies. Where there was slightly less, matter was drawn away, leaving regions that grew thinner and emptier with every passing age. These emptier regions are what we now recognize as cosmic voids. The story of voids is, in many ways, the story of time itself. Unlike the bright stars that live for millions or billions of years before dying in spectacular explosions, voids do not burn or collapse or shatter. They simply stretch. They expand with the growth of the universe, and they deepen as gravity pulls more and more matter away toward denser regions. In this sense, voids are the quiet witnesses of cosmic time, showing us how the universe has changed since its fiery birth. In the early universe, perhaps only a few 100 million years after the Big Bang, galaxies began to form. Already the seeds of voids were present. Regions that contained less matter than average started to expand faster than their surroundings, because they were not weighed down by as much material. Imagine two balloons, one filled with heavy grains of sand and the other with only a handful. When both are stretched, the lighter balloon expands more easily, becoming thinner and more spread out. In the same way, the less crowded regions of the early universe spread apart more quickly than the denser regions. Over the course of billions of years, this difference became dramatic. The dense regions grew into the rich galaxy clusters and filaments we see today, while the empty regions stretched into the vast voids. Time also allowed for an astonishing growth in size. Today, some of the largest voids, like the Bootes void, are more than 300 million light-years across. To imagine such a scale is almost impossible. A single light-year is the distance light travels in 1 year, moving at nearly 300,000 kilometers per second. Multiply that by hundreds of millions, and you begin to sense the vast emptiness carved by time. Yet these gigantic regions did not appear all at once. They began as small underdense areas in the infant universe, slowly stretching as the ages passed. Over 10 billion years or more, they grew from small hollows in the cosmic fabric into yawning spaces that dominate the large-scale structure of the universe. The growth of voids is not only about expansion, but also about the draining effect of gravity. Time has given gravity countless ages to act like a cosmic magnet, drawing matter away from the underdense regions into the overdense ones. Every billion years that passed, galaxies that might once have been on the edge of a void drifted closer to a filament or cluster, leaving the void even emptier. Gas, too, has flowed away over time, feeding star formation in denser areas and starving the voids. In this sense, time has worked both ways. It has stretched the voids outward and also hollowed them from within. What makes this process so fascinating is that it is still happening right now. The voids we see today are not finished. They are still stretching as the universe continues to expand. In fact, the expansion of the universe itself, which has been accelerating for the past few billion years due to dark energy, is giving voids an even greater push. In the far future, perhaps tens of billions of years from now, voids may dominate the structure of the universe even more strongly than they do today. Galaxies may drift so far apart that entire regions of the sky will seem almost completely dark, with only the faintest traces of matter left in between. Time is therefore the great engine behind the growth of voids, but it also gives us a way to study the history of the universe. When astronomers look into the night sky with powerful telescopes, they are not just seeing objects as they are now, but as they were in the past. Light from distant galaxies takes millions or billions of years to reach us, so each view is like a time machine. By studying galaxies at different distances, astronomers can piece together how voids have changed over time. In the early universe, voids were smaller and less pronounced, but as billions of years passed, they grew into the giant structures we see today. The role of time can be read in these observations like words on a page, telling the story of emptiness expanding. It is worth remembering that voids are not completely empty, even after billions of years of growth. Time has stretched them so much that matter inside them is thin and scattered, but it is not gone. Some faint galaxies remain inside, often smaller and more isolated than their cousins in denser regions. Streams of gas still drift through the darkness, though far less than in rich clusters. Even dark matter, which makes up most of the universe's invisible mass, is spread thin across voids. These lonely bits of matter are like the last echoes of what once might have been, preserved by time but made faint by the relentless stretching of space. Time has also revealed another curious fact. Voids are not just empty regions, but active participants in the cosmic dance. As they expand, they push against the filaments and walls of galaxies around them, helping to shape the cosmic web. It is as if the universe is being pulled and pushed at once. Gravity pulls matter into clusters, while time-driven expansion of voids pushes against those same clusters, sharpening the boundaries between light and darkness. This tension, played out over billions of years, is one of the main reasons the universe has its beautiful sponge-like pattern of filaments and hollows. The idea of time-shaping voids also invites us to imagine the future. If we could leap forward by tens of billions of years, what would we see? Many astronomers believe that voids will become even more dominant. The galaxies that remain inside them may drift farther apart, their light fading until they are almost invisible. The filaments themselves may thin, as dark energy drives galaxies away from one another at increasing speeds. Time will not only stretch voids, but may eventually leave them as nearly absolute emptiness, broken only by the occasional dying galaxy stranded in the dark. The idea may sound almost unbelievable at first, yet it is true that our own Milky Way galaxy, the great island of stars that we call home, is not sitting in the busiest part of the universe. Instead, it rests within a quieter zone, a smaller cosmic void where there are fewer galaxies than in the more crowded regions of space. To many people, the word void makes them think of a place that is totally empty, but in reality, cosmic voids are not absolute nothingness. They are vast stretches of the universe where matter is thinner, where galaxies are less frequent, and where space is opened wider than in other regions. The surprising fact that our Milky Way lies inside such a region adds a fascinating twist to our understanding of the universe, because it means that even our own cosmic neighbourhood is shaped by these immense patterns of emptiness and clustering. When astronomers first discovered cosmic voids, they imagined them as enormous black bubbles scattered throughout the cosmic web. These bubbles, sometimes stretching hundreds of millions of light years across, looked as if someone had carved giant hollow spaces in the universe. Galaxies were seen mostly on the edges, lining the walls and filaments like dew on a spider's web, while the interiors appeared much emptier. What shocked scientists later was realizing that the Milky Way itself, along with the galaxies that are closest to us, sits inside one of these underdense regions. It is not one of the largest voids, like the famous Bootes void, which spans over 300 million light-years across, but it is a smaller cousin, still large enough to influence how galaxies, matter and light behave in our part of the cosmos. To understand what it means to live in a void, it helps to think about how matter is distributed in the universe. In the earliest times, shortly after the Big Bang around 13.8 billion years ago, the universe was hot, dense, and almost uniform. Tiny fluctuations in density existed. Some places had just a little more matter than others, and some had slightly less. As the universe expanded and cooled, gravity began to pull more strongly in the denser regions, drawing gas and dark matter together to form galaxies and clusters. Meanwhile, the less dense regions expanded faster, pushing their few contents farther apart. Over billions of years, this difference grew stronger, leading to today's striking picture of a universe shaped like a cosmic web, clusters and filaments filled with galaxies, separated by great gaps of emptiness that we now call voids. Our Milky Way is located inside such a void, which astronomers have named the local void. This local void is not as enormous as some of the great cosmic hollows, but it still measures at least 150 million light-years across in certain directions, though its shape is irregular and hard to measure precisely. To put this in perspective, our entire galaxy is about 100,000 light-years across, so the local void dwarfs it by over 1,000 times. Within this vast region, galaxies are fewer in number compared to surrounding areas, and there is a sense of thinness in the cosmic population. The local void borders other structures, including the Virgo cluster, which is a dense gathering of galaxies about 60 million light-years away. This means that while we live in a more spacious and underfilled region, we're also not too far from a bustling galactic city. the presence of the Milky Way in a void has many consequences. For example, it helps explain some of the peculiar motions of our galaxy. Astronomers have observed that the Milky Way is not simply drifting with the smooth expansion of the universe, known as the Hubble flow, but it also has additional motions caused by gravitational pulls and pushes. One of these influences comes from the local void itself. Because the void has less matter than surrounding regions, it exerts less gravitational attraction. In a way, the Milky Way is being pulled away from the emptiness and toward the denser zones like the Virgo cluster and the Great Attractor, which is a massive concentration of galaxies about 250 million light-years away. This motion, sometimes called a repulsion from the void, is not an actual force pushing us, but rather the result of gravitational imbalance between the emptiness and the density of the universe's structures. Scientists studying the local void have found that it is not a perfectly simple structure. It is lopsided, stretched, and interconnected with other nearby voids, forming a network of emptiness just as galaxies form a network of filaments. This shows us that voids are not isolated bubbles floating in the universe, but part of the overall cosmic pattern. Each void influences the motion of galaxies around it, and together they help shape the large-scale dynamics of the cosmos. Living inside a void, therefore, means that our galaxy is taking part in this grand dance of gravitational flows, drifting away from emptiness and toward density over billions of years. Another surprising fact is that being inside a void may have affected how galaxies like the Milky Way developed. In denser environments, galaxies interact and collide more often, which can lead to rapid bursts of star formation, or in some cases the stripping away of gas that fuels stars. In a quieter region like the local void, interactions are less frequent, meaning that galaxies might have evolved in a calmer, more gradual way. This could help explain why the Milky Way has had a steady star-forming history for billions of years, rather than burning through its gas supply too quickly. The emptiness around us may have given our galaxy more room and time to grow in a balanced way, avoiding the harsher conditions of galactic clusters. Astronomers use many tools to map out the local void and to measure its properties. One of the most important techniques is looking at the redshift of galaxies, which reveals how fast they are moving away due to the expansion of the universe. By comparing the redshift to their actual distances, scientists can detect unusual motions that signal the presence of voids and other large structures. In the case of the local void, galaxies on its boundary seem to be flowing outward, as if sliding away from the emptiness and toward denser regions. This outward flow is one of the strongest signs that the void exists and that it affects galaxy motions on a grand scale. The discovery of the local void also reshaped our view of the cosmic neighborhood. For many years, astronomers focused mainly on clusters and groups of galaxies, thinking of the universe as a set of islands of matter. But when they realized that large voids, including the one we inhabit, are essential pieces of the puzzle, it changed the story. It showed that the universe is not just made of what is there, but also of what is missing. The absence of matter, the spaces between galaxies, plays just as big a role as the presence of galaxies themselves. By living in a void, the Milky Way is an example of how emptiness can shape destiny just as much as fullness. It is also fascinating to consider how different the night sky might look if our galaxy were located in a denser region instead of a void. In a cluster, the sky would be filled with bright galaxies shining close together, some visible even to the naked eye. Collisions and mergers would be common, and the environment would be far more chaotic. Instead, our galaxy sits in a relatively quiet neighborhood, where the nearest large galaxy, Andromeda, is about 2.5 million light-years away. This distance gives us peace, cosmic breathing room, and perhaps even the chance for life to develop undisturbed over billions of years. In this sense, living in a void may not just be a scientific curiosity, but also a cosmic blessing. The concept of voids also raises deep questions about the nature of dark matter and dark energy. Since voids are regions where visible matter is scarce, they provide unique laboratories for studying the invisible components of the universe. By examining how galaxies flow around voids, astronomers can test theories about how dark matter is distributed and how dark energy drives the expansion of space. Some studies even suggest that voids are especially sensitive to the effects of dark energy, making them powerful tools for understanding why the universe's expansion is accelerating. In this way, the local void, though relatively small, is part of a much larger quest to understand the forces that shape everything, Another layer of interest comes from comparing the local void to other cosmic voids. The Bootes void, discovered in the 1980s, remains one of the largest known, spanning more than 300 million light-years. Inside it, only a few dozen galaxies have been found, when thousands would be expected. Compared to such giants, the local void may seem modest, but it is still large enough to matter. Its influence on the motion of the Milky Way and surrounding galaxies is undeniable, and its presence shows that even small voids can play important roles in the cosmic structure. It is worth noting that voids are not completely empty. They contain stray galaxies, wisps of gas, and of course, dark matter, which makes up most of the mass in the universe. The density is simply lower than average. For example, while the average universe might have a certain number of galaxies per volume of space, a void may have only 1/10 or even 1/100th of that number. This sparseness is what defines them. In the local void, a few galaxies do float in the emptiness, lonely travellers in a vast desert of space. Their isolation makes them unusual and important to study, since they reveal how galaxies behave without the constant influence of neighbours. The Milky Way's position on the edge of the local void also gives astronomers a unique viewpoint. It allows them to look outward into both emptiness and density, comparing the two sides of our cosmic environment. This comparison helps refine measurements of the Hubble constant, which describes the rate of cosmic expansion. Some scientists have even suggested that our location in a void might slightly affect these measurements, potentially helping explain why different methods of calculating the Hubble constant sometimes give conflicting results. Though this idea is debated, it shows how living in a void may touch upon some of the deepest mysteries in cosmology. The story of the local void is still unfolding. New surveys using advanced telescopes continue to map galaxies more accurately, giving sharper pictures of where the boundaries of the void lie. Computer simulations also allow scientists to recreate the growth of voids over billions of years, showing how tiny fluctuations in the early universe grew into the vast emptiness we see today. These simulations suggest that voids are not merely byproducts, but essential structures in the cosmic web, giving the universe its shape and flow. The local void, where we live, is just one thread in this intricate design. If we imagine what it means for humanity, the thought that our galaxy resides in a cosmic void adds to the sense of wonder about our place in the universe. We're not in the heart of a shining cluster, nor at the centre of some great structure. Instead, we live in a quieter corner, on the edge of a vast emptiness, where the stars still shine brightly but the galaxies are spread thin. This solitude may have given us the stability and calm needed for life to appear, and for civilizations to grow, allowing time to wonder, to question, and to look back into the voids that shaped us. It is almost impossible for the human mind to picture true nothingness, yet in the universe there are vast stretches where galaxies are rare, where gas is scarce, and where stars are almost absent. These extraordinary empty spaces are what scientists call cosmic voids. Some are small compared to the size of the universe, though even the smallest void would dwarf entire clusters of galaxies. Others, however, are so large that they stretch across billions of light-years, making them the record holders for the most immense regions of emptiness ever discovered. These largest known voids are not simply curious features of the universe. They are like gigantic fingerprints left by the forces that shape the cosmos since its very first moments. Their sizes, their shapes, and their strange loneliness tell us about how matter moved, gathered, and spread across the great ocean of space. To stand in imagination inside one of these enormous voids is to feel smaller than one could ever imagine, because here the universe shows its truest scale of emptiness. The story of the largest known voids begins not in the modern age, but billions upon billions of years ago, shortly after the birth of the universe. In those first moments, the universe was nearly smooth and uniform, filled with energy and particles spread almost evenly in every direction. But perfection was not complete. There were tiny irregularities, faint ripples of matter and energy slightly denser in some places and slightly thinner in others. Over unimaginable stretches of time, these small differences grew. The regions with just a little more matter pulled in even more matter through gravity, becoming the homes of galaxies, clusters, and superclusters. The regions with slightly less matter lost even more as the denser neighbours drew matter away, leaving behind wide gaps that would grow into the enormous voids we now measure across billions of light-years. Among these record-breaking empty regions, one name is often whispered with awe: the Bootes void. This immense hollow in space is sometimes called the Great Nothing. Discovered in the early 1980s by astronomers who were mapping galaxies in the northern skies, it immediately stunned the scientific world. The Bootes void is roughly 700 million light-years across from one side to the other, a distance so overwhelming that if one could travel at the speed of light, the fastest possible speed in the universe, it would still take 700 million years to cross from edge to edge. To compare, our entire Milky Way galaxy is only about 100,000 light-years wide. That means the Bootes void is about 7,000 times wider than the Milky Way. Inside such a region, one might expect nothing at all, pure blackness without a single flicker. Yet when astronomers examined it more carefully, they did find a few galaxies scattered like lonely ships floating on an endless dark sea. Estimates suggest there may be only around 60 galaxies in this whole void. In other regions of the universe of equal volume, there would normally be thousands upon thousands of galaxies. The Bootes void is so strikingly empty that it has become a symbol of cosmic loneliness. But the Bootes void is not the only record holder. Other vast voids have been discovered that rival or even surpass it in size. One of these is the KBC void, sometimes simply called the local hole, discovered by a group of astronomers named Keenan, Barger and Cowie in the year 2013. This void is centered near our own cosmic neighborhood. In fact, our Milky Way and its surrounding galaxies may actually lie inside the edges of this immense hollow. The KBC void is estimated to be nearly 2 billion light-years across, making it even larger than the Bootes void. This discovery was surprising because it suggested that we ourselves live in a less crowded part of the cosmos than we once thought. If true, it changes the way astronomers measure the rate at which the universe is expanding, because the emptiness around us might affect the light from distant galaxies, giving us slightly distorted impressions of cosmic speed and distance. Going further into the deep night sky, astronomers have mapped other titanic voids. The Giant Void, located in the direction of the constellation Canes Venatici, is another breathtaking region of emptiness. This void measures around 1.5 billion light-years across, though different methods of measurement give slightly different values. The Giant Void is so large that it has been described as one of the most massive structures of emptiness known. Yet despite its frightening size, it too contains some galaxies, for even the largest voids are not completely empty. They are underdense, meaning they have far less matter than average, but they still host traces of galaxies, faint gas, and perhaps mysterious dark matter that cannot be seen directly. The discovery of these record-breaking voids has reshaped how we picture the cosmic web. The universe is not simply a smooth soup of stars and galaxies. It is instead structured like a vast web or sponge. The filaments of this web are long, thread-like chains of galaxies and clusters bound together by gravity. At the junctions of the filaments are enormous galaxy clusters, shining like bright knots of jewels. But in between these filaments and knots are the voids, where very little matter exists. When mapped in 3 dimensions, the universe looks like foam, galaxies outlining the surfaces of bubbles, with the insides of the bubbles representing the voids. The largest of these bubbles can span billions of light-years. Standing within them would feel like being in a cavern so large that no end could be seen, a cavern where the stars are so rare they feel like lonely sparks scattered in the dark. One of the reasons these enormous voids are so fascinating is that they allow scientists to test theories about how the universe has expanded and evolved. When astronomers look at the distribution of galaxies across the sky, they can use voids as natural laboratories. The shapes and sizes of voids tell us how dark energy, the mysterious force driving the accelerated expansion of the universe, has influenced cosmic growth. If voids grow faster than expected, it might hint at new physics beyond what we currently know. Observing record-breaking voids helps researchers measure how gravity, dark matter, and dark energy all interact on the largest scales possible. In other words, these hollow regions are not simply dead zones. They are keys to unlocking the universe's greatest secrets. To bring this closer to human imagination, consider what it would be like to float inside the Bootes void. You would see galaxies only every few 100 million light-years, tiny smudges of light so distant they appear like fireflies spread thin across an endless night. If our Milky Way were placed in the center of the Bootes void, it would have almost no nearby galaxies to interact with. Galaxies usually live in neighborhoods where gravity pulls them toward each other, where they merge and collide and shape one another's growth. In the Bootes void, however, our galaxy would drift almost alone, with no major encounters to stir its stars. The sense of isolation would be staggering. It would be like living in a vast desert where only a handful of oases exist, each separated by an impossible distance. Even more staggering is to consider how small we are in relation to these cosmic hollows. The Earth is a mere 13,000 kilometers wide. The Sun is about 1.5 million kilometers across. Our Milky Way galaxy, as already said, is 100,000 light-years in diameter. Now place this against the Bootes void, 700 million light-years across, or the KBC void, almost 2 billion light-years across. The numbers are beyond comprehension. They make the human world, with all its oceans and mountains, seem no larger than a grain of sand. Yet these voids are not just curiosities. They have real effects on how we understand the cosmos. For instance, the KBC void may influence the Hubble tension, which is the current disagreement among astronomers about how fast the universe is expanding. If our galaxy sits inside a void, then the light travelling from galaxies beyond the void is slightly altered as it moves through less matter. This could make them appear to be moving away from us faster than they truly are. Thus, the discovery of a record-breaking void in our cosmic neighbourhood might help explain why different methods of measuring cosmic expansion give different answers. In this way, emptiness itself might hold the solution to one of the greatest puzzles in astronomy. The mapping of these enormous voids has been made possible by galaxy surveys that stretch across vast portions of the sky. In the late 20th century, astronomers began to map galaxies in 3 dimensions, rather than just recording their positions as dots of light. By measuring the redshift of each galaxy, which reveals how fast it is moving away due to cosmic expansion, they could calculate distances. When thousands upon thousands of galaxies were plotted in this way, an astonishing picture emerged. Instead of being randomly scattered, galaxies lined up into filaments and sheets surrounding vast empty regions. These regions were the voids, and the largest of them leapt out as record-breaking hollows where almost no galaxies existed. The Bootes void was one of the earliest such discoveries, and it remains one of the most famous. But as surveys became larger and more detailed, astronomers found voids that were even more impressive in size. The existence of such immense hollows also challenges the human imagination in a philosophical sense. People are accustomed to thinking of space as filled with stars. Looking up at the night sky, one sees countless points of light. But in reality, the universe is mostly empty. The largest voids emphasize this truth with brutal clarity. Imagine billions of light-years of space containing almost nothing. These voids are not merely dark, they are profoundly silent. No civilizations would flourish in them, no rich clusters of stars would shine, no bustling galaxies would interact. They are the deserts of the cosmos, barren and cold, yet they are also part of the balance that allows the cosmic web to exist. Without voids, the filaments of galaxies would not be as pronounced. The emptiness gives shape to the fullness. The darkness makes the light stand out. In some cases, the largest voids have been linked with other cosmic mysteries. For example, there is the CMB cold spot, a strange region on the map of the cosmic microwave background radiation that appears cooler than its surroundings. Some scientists have suggested that this might be explained by the presence of a massive void along that line of sight, perhaps hundreds of millions of light-years across. The idea is that as light from the early universe passes through such a void, it loses energy in a way that makes it appear colder when it finally reaches us. While this explanation remains debated, it shows how voids may connect to some of the strangest puzzles about the very birth of the cosmos. The largest known voids also raise questions about the ultimate fate of the universe. As time passes, galaxies continue to move apart, and voids continue to grow. In the far future, billions of years from now, these voids may dominate the cosmos even more strongly than they do today. The filaments of galaxies will become thinner, and the clusters will drift farther apart, leaving even larger gaps between them. The record-breaking voids of today may be dwarfed by even vaster hollows in the future. Eventually, the universe could become so spread out that almost every observer, living in some distant galaxy, would see only darkness, unable to detect the rest of the cosmic web. The voids would have swallowed the visible universe, leaving loneliness as the defining feature of reality. Yet in all this, there is a strange beauty. The largest voids, despite being nearly empty, give shape to the cosmic architecture. Without them, the web of galaxies would not form its lace-like patterns. They are the silent stage upon which the drama of stars and galaxies is played. In the same way that silence gives meaning to music, These immense voids give meaning to the shining filaments of galaxies. The Bootes void, the giant void, the KBC void, and others like them are reminders that emptiness can be as significant as presence. The largest known voids, stretching across billions of light years, show that the universe is not simply about what exists, but also about what does not exist. The balance between fullness and emptiness is what shapes the cosmos into the vast, wondrous structure we see today. Far away in the deep ocean of space, there are places that look very dark, like great hollows spread between the galaxies. To anyone who looks at them through a telescope, these dark regions may appear as though they are enormous black patches, almost as if parts of the universe were missing. Because of this appearance, many people easily compare them to black holes, those mysterious monsters of gravity that swallow everything in their reach. At first glance, the comparison feels natural, since both appear as areas of darkness against the glittering background of stars and galaxies. Yet the truth is that these two kinds of blackness in space are very different. One comes from the simple absence of light-emitting objects, while the other is caused by gravity so strong that even light itself cannot escape. Understanding how these black spaces differ from black holes not only clears confusion, but also opens a window into the way the universe is built and how different cosmic structures interact with one another. When we speak of black holes, we are speaking of some of the most extreme objects ever imagined by science. A black hole forms when matter is compressed into such a tiny space that its gravitational pull becomes overwhelming. No star, no planet, no beam of light can escape once it gets too close. The edge of this region, called the event horizon, is like a point of no return. Cross it, and there is no escape. This is what makes black holes so famously terrifying and fascinating at the same time. They are not just empty space, they are dense, compact, and full of energy. In fact, a single black hole may weigh as much as millions or even billions of suns. They bend light, twist space, and warp time around them. They are true abysses in the fabric of the universe. The black spaces, however, are something else entirely. These are cosmic voids, vast regions that look dark not because of overwhelming gravity, but because they contain so few galaxies compared to other regions. They are like deserts in the cosmic landscape, not monsters waiting to devour everything. A void can stretch across hundreds of millions of light years, making it far larger than any black hole, but it is not dangerous in the same way. If one could travel into a cosmic void, nothing unusual would happen to you. You would not be stretched, crushed, or pulled apart. You would simply find fewer galaxies around, fewer stars shining, and a lot more empty space. This is the first big difference between black holes and black spaces. One is crowded and dense, the other is empty and thin. In a black hole, matter is squeezed into a very small region. In a cosmic void, matter is spread so thinly that it almost seems to disappear. A black hole is about crushing everything into one point, while a cosmic void is about stretching everything far apart. The second difference is in how light behaves. In a black hole, light cannot escape. That is why they appear as perfect darkness, even against the brightness of surrounding stars. In cosmic voids, light is not trapped but simply absent. The voids look black because there are very few galaxies there to shine. If you were to shine a flashlight in a void, the beam would pass through just as it would anywhere else in the universe. There is nothing there to stop it. A black hole is a prison for light, while a void is simply an empty stage without many lights switched on. Size also plays a huge role in separating the two. A typical stellar black hole formed from the death of a massive star might be a few tens of kilometers across. Even a supermassive black hole at the center of a galaxy, like the one in the heart of the Milky Way, is only as wide as the orbit of our solar system. Compare this with cosmic voids, which can span hundreds of millions of light years. Imagine the difference. A black hole could swallow a star or even a cluster of stars, but a void is large enough to surround thousands of entire galaxies and still feel mostly empty. Voids are the largest structures of emptiness in the universe, while black holes are small in size but immensely powerful in their effect. Another striking difference lies in their origin. Black holes form from collapsed stars or from regions where huge amounts of matter fall inward and collapse under their own weight. Their story is about gravity pulling things together. Cosmic voids have the opposite story. They began as small regions in the early universe that contained slightly less matter than their neighbours. As the universe expanded, those emptier regions stretched more quickly than the denser ones. Over billions of years, this made them emptier and larger, until they became the enormous voids we see today. One is born from collapse, the other from expansion. If you think about what would happen to a traveller who ventures into each of these places, the difference becomes even more dramatic. A spaceship approaching a black hole would experience something terrifying called spaghettification. As it nears the event horizon, gravity pulls more strongly on the part of the ship closer to the black hole than on the far side. This difference in pull would stretch and tear the ship apart, turning it into a long stream of matter before it disappears forever. Entering a void, by contrast, would feel no different from drifting through any other part of space. The stars would simply become scarcer, and the darkness would seem deeper. There would be no crushing forces, no sudden death, only emptiness. One might also compare how scientists detect these two phenomena. Black holes cannot be seen directly because they do not let light escape. Instead, astronomers detect them by their effects on their surroundings. A black hole pulling gas toward itself can heat the gas until it glows in X-rays. Stars orbiting an invisible point reveal that something incredibly heavy must be hiding there. Voids, however, are detected not through violence but through absence. Astronomers map galaxies across the universe and notice huge patches where very few galaxies are found. By measuring the distribution of galaxies, they can outline the vast hollows of the cosmic web. Even the way these two entities interact with the larger universe is different. Black holes are engines of energy. The matter swirling around them can release more power than millions of suns, shooting out jets of particles that stretch for thousands of light years. They are not silent monsters. They roar with activity. Voids, on the other hand, are quiet. They do not roar, they do not feed, and they do not spit out jets. They are like calm, empty valleys between the mountains of galaxy clusters. Another important distinction lies in how they shape time. According to Einstein's theory of general relativity, gravity warps time. Near a black hole, time slows down compared to regions farther away. This effect becomes extreme near the event horizon, where an outside observer would see time nearly freeze for someone falling in. Cosmic voids, with their low density, have the opposite effect. The weaker gravity there means that time runs slightly faster compared to regions with more matter. This difference may seem tiny, but over billions of years it adds up and influences the way cosmic structures grow. In a sense, black holes drag time backward, while voids let it slip forward a little quicker. It is also fascinating to think about how people's imaginations treat these two. Black holes have long been symbols of destruction, terror, and ultimate mystery. Science fiction often paints them as gateways to other universes or deadly traps. Cosmic voids, though less famous, have their own kind of eerie poetry. They represent loneliness on a cosmic scale, an emptiness so vast it defies human imagination. If black holes are thought of as cosmic predators, voids might be seen as cosmic deserts, endless stretches where very little lives. The contrast continues when we look at energy. A black hole, especially a supermassive one, can be the most luminous object in the universe when it is actively feeding. The material falling into it releases more energy than all the stars in a galaxy combined. Voids, in contrast, are not sources of energy at all. They are simply where energy and matter are not. This makes them look dark and silent, but they still play a huge role in the cosmic balance by surrounding and shaping the brighter, denser regions. Consider also the way scientists think of them as tools for studying the universe. Black holes are laboratories for extreme physics, where theories of gravity, quantum mechanics, and thermodynamics are pushed to their limits. They challenge us to unite all of physics into one grand theory. Voids, meanwhile, are laboratories for understanding the universe's expansion, dark energy, and the overall shape of the cosmos. By studying the emptiness of voids, scientists can test how fast the universe is growing and how matter is spread on the larger scales. Both are valuable, but in very different ways. While both black holes and cosmic voids seem mysterious, the kinds of questions they raise are different. With black holes, we ask what happens at the singularity, the point where density becomes infinite and our laws of physics break down. With voids, we ask what role dark matter and dark energy play in shaping such vast empty spaces. One mystery is about the tiniest point in space, the other about the largest stretches of it. The difference is so striking that if someone mistook one for the other, they might completely misunderstand the nature of the universe. If you looked at a void and thought it was a black hole, you might believe there was a monster devouring entire galaxies, but really it is only a quiet hollow left behind as matter gathered elsewhere. Similarly, if you thought a black hole was just empty space, you would miss its immense power and danger. It is not just an absence, but a presence so strong it bends the universe around it. And yet, despite their differences, these two opposites, one of extreme density and one of near emptiness, are connected in a beautiful way. The cosmos is not uniform, not the same everywhere. It contains monsters of gravity and deserts of nothingness, each shaping the universe in its own way. One teaches us about collapse, the other about expansion. One hides secrets at the smallest scale, the other at the largest. Together they show that the universe is full of contrasts, balancing fullness with emptiness, violence with silence. All around us, the universe stretches outward like an endless ocean, whose waters are not calm but are moving, pushing and spreading farther with every passing moment. What is even more puzzling is that this expansion is not slowing down, as one might expect from the pull of gravity, but is instead speeding up. It is as if some unseen hand is gently pushing galaxies apart, making the universe grow faster the more time passes. This strange force has been given a name: dark energy. Though the word sounds mysterious and almost poetic, it is actually just a placeholder for something that scientists cannot yet fully explain. They do not know what dark energy truly is, only that it must exist to account for what is being observed. And among the places where the clues about dark energy become most striking are the immense cosmic voids, those giant empty regions of space that seem to stretch across hundreds of millions of light years with hardly any galaxies inside them. To stand on Earth and imagine such emptiness is nearly impossible. Our world feels full of air, of water, of mountains, of trees, and of the crowded hum of human life. Even the night sky when we gaze upward looks filled with stars. Yet astronomers have discovered that when we zoom out far enough, the universe is not uniformly filled with galaxies. Instead, it looks like a gigantic web. Galaxies, clusters and superclusters are strung together along filaments of matter, like shining beads on invisible threads, and between these threads are vast hollow regions, the voids. These voids are not truly empty, for they still contain thin traces of matter, a few stray galaxies and ghostly wisps of gas. But compared to the cosmic filaments, they are astonishingly bare. And it is in these near-empty spaces that the fingerprints of dark energy can be seen most clearly. The discovery of cosmic voids is relatively recent in human history. For centuries, astronomers thought of the universe as either filled with stars or perhaps infinite in all directions without any significant structure. It was only in the 20th century, as surveys of the sky became more detailed, that scientists noticed patterns. By mapping the positions of galaxies across enormous stretches of space, they began to see that galaxies were not randomly scattered, but arranged in a foamy, web-like pattern. The first hints of these vast voids appeared in the 1970s and 1980s, when astronomers realized that certain regions spanning tens or even hundreds of millions of light years contained shockingly few galaxies. One of the most famous of these is the Butter's Void, discovered in 1981. It spans almost 330 million light-years across, a bubble of near emptiness so large that if our own galaxy were placed inside it, we might see only a handful of galaxies in the entire sky instead of the thousands we see now. What makes these voids so interesting in the search for answers about dark energy is the way they expand. Gravity acts to pull matter together. Where matter is dense, such as in clusters of galaxies, gravity slows the outward movement, trying to hold things in place. But in voids, there is little matter to exert this pull. Instead, the repulsive effect of dark energy becomes more obvious, stretching the voids wider and faster than other regions of space. To think of it in simpler terms, imagine bread dough filled with raisins. As the dough rises and expands, the raisins move apart. In the dense clumps of dough, the raisins may move only slightly, but in the airy, thin parts of the dough, the raisins drift far apart very quickly. The voids are like those airy regions of the dough, swelling more than the denser regions because there is less to counter the expansion. Astronomers study these voids like detectives studying fingerprints. The exact size of a void, the rate at which it grows, and the way light bends and moves through it, all provide valuable evidence about what dark energy might be. Because voids are more sensitive to expansion than clusters, They act almost like magnifying glasses for dark energy, amplifying its effects so that scientists can measure them more precisely. Some have even said that voids are the most natural laboratories for testing the mysteries of cosmic acceleration. Unlike galaxy clusters, which are complicated by countless gravitational interactions, voids are simpler, cleaner places where the influence of dark energy is laid bare. It may seem strange to imagine that emptiness could tell us more than fullness, but in the case of cosmic science, this is exactly true. In the crowded regions of space where thousands of galaxies tug on one another, it is hard to untangle what comes from gravity and what comes from dark energy. But in the quiet stillness of the voids, the story becomes clearer. Scientists can measure the way galaxies at the edge of a void drift away, pulled not so much by one another, but pushed outward by the accelerated swelling of space itself. This has led to an entire field of research known as void cosmology. Observations from powerful surveys, such as the Sloan Digital Sky Survey, and later missions that mapped millions of galaxies, have allowed researchers to trace the outlines of these voids with remarkable precision. By measuring the clustering of galaxies and the size of the spaces between them, they can compare the observations with predictions made by different models of dark energy. If the universe behaved only under the influence of gravity and normal matter, the voids would not grow as large or as quickly as they do. The fact that they do suggests that some other force, dark energy, must be at work, driving the expansion forward. One of the most fascinating aspects of this connection is that voids also affect the light travelling through them. When light from distant galaxies or the afterglow of the Big Bang, the cosmic microwave background, passes through a void, it can be stretched, cooled, or shifted in subtle ways. These shifts, known as the integrated Sachs-Wolf effect, offer another way of detecting the presence of dark energy. Essentially, light passing through a vast emptiness experiences the accelerated expansion more directly, leaving faint but measurable imprints in its journey. By carefully studying these patterns, astronomers can refine their understanding of how dark energy operates across cosmic history. The very idea that dark energy might make up nearly 70% of the entire universe is staggering. To think that most of reality is controlled by something invisible and unexplained is both thrilling and unsettling. We can measure its effects but not touch it, not bottle it, not even fully describe it. The voids give us one of the clearest windows into its existence, but they do not yet tell us what it actually is. Some scientists imagine it as a property of space itself, a kind of vacuum energy that causes expansion. Others suggest it may be connected to new, undiscovered fields or particles, or even that it hints at flaws in our understanding of gravity on cosmic scales. What is certain is that without dark energy, the universe would look very different. If only gravity and normal matter were at work, cosmic expansion would have slowed after the Big Bang, perhaps even collapsed back inward after billions of years. Instead, in the late 20th century, astronomers measuring the brightness of distant exploding stars, supernovae, made the shocking discovery that the universe's expansion was not slowing but accelerating. This revelation in 1998 earned researchers the Nobel Prize and transformed cosmology. Since then, voids have become some of the best testing grounds to verify and refine this picture, because they are the regions where the accelerated stretching of space shows itself most dramatically. If one could travel into one of these cosmic voids, the experience would be both haunting and beautiful. The journey would take us far from the familiar sight of clustered galaxies. Instead of skies filled with countless stars, we might see only a handful, lonely and faint, scattered across an overwhelming black canvas. The sense of isolation would be immense. Yet this isolation is precisely why voids are so valuable. They show us space in its purest, most unburdened form. They let us see the tug-of-war between gravity and dark energy without much interference. And the result of that contest over billions of years has been that dark energy wins. The voids grow ever larger, and the web of the universe stretches ever thinner. The thought that our own galaxy resides in a region that is itself somewhat emptier than average only adds to the intrigue. The Milky Way and its neighbours in the local group lie within what is sometimes called the local void, a smaller underdense region of space. Though not as vast as the Boötes void, it still influences the motions of galaxies around us, and reminds us that emptiness is not a distant phenomenon, but a feature of the cosmic landscape we inhabit. Studying the local void helps astronomers test theories on a smaller, more approachable scale, while still connecting to the grander picture of dark energy and universal expansion. Over the coming decades, new observatories and missions are set to map these voids with unprecedented detail. Projects like the Euclid Space Telescope, the Vera C. Rubin Observatory, and the Nancy Grace Roman Space Telescope are designed to capture enormous amounts of data about the distribution of galaxies and the geometry of the universe. With these tools, scientists hope to measure dark energy not just as a single mysterious force, but in terms of its possible evolution across time. Did dark energy always have the same strength, or has it changed since the birth of the universe? Are we dealing with a constant property of space, or a dynamic energy field that shifts over billions of years? Voids may provide the clearest path to answering these questions, because they amplify the very effects that astronomers are trying to measure. Over the course of billions upon billions of years, an invisible but relentless force began to shape the universe in quiet patience. That force was gravity. It did not rush, it did not thunder loudly, it simply pulled, steadily and persistently, wherever there was just a little more matter than average. In certain places, where dark matter was slightly denser, gravity tugged at the surrounding material. Bit by bit, grain by grain, it gathered more of the universe's substance into those spots. This slow but unstoppable process is known as gravitational instability. Tiny lumps of dark matter grew larger over time, becoming heavier as they collected more material around them. Imagine little seeds buried in the soil of the early cosmos, each one swelling as more dirt clung to it. Those seeds eventually grew into vast and invisible halos of dark matter. You can think of these halos like deep wells carved out by gravity, or like massive unseen mountains whose peaks could not be touched by light. Within these invisible structures, ordinary matter, gas, dust, and the building blocks of everything we see began to fall and gather. As the gas cooled and clumped more tightly together, it ignited into the very first stars. Over time, those stars linked into the first galaxies, blazing islands of light in an ocean of darkness. Even now, the galaxies we see with our telescopes are still sitting inside those ancient dark matter halos. They remain trapped and held in place by the same gravitational arms that shaped them long ago. If you picture the universe as an enormous construction project, dark matter is the hidden scaffolding, the framework that everything else clings to. Without it, galaxies would drift apart, unable to form the great chains of clusters and the astonishing filaments that stretch for billions of light years across the cosmos. If dark matter had not existed, the universe would have been unrecognizable. The ordinary matter made of atoms, what we can touch, measure, and see, does not have enough gravitational pull on its own to overcome the powerful expansion that began after the Big Bang. Without the helping hand of dark matter, matter would have remained thinly spread, forming only a faint, misty soup of gas. No brilliant galaxies, no shining stars, no intricate structures would have ever appeared. The universe would have been a dull and empty place. But dark matter did more than just gather material to form galaxies. It also carved out the deep, quiet spaces in between. These vast empty regions are called cosmic voids. One of the most famous of them is the Bootes void, a gargantuan hole in the cosmic web. Just as some places had slightly more dark matter, other regions had slightly less. Where there was less dark matter, gravity was weaker. As matter was pulled into the denser neighborhoods, these poorer regions were left behind, slowly drained of their contents. Imagine the early universe as a giant drainage system. The denser pockets of dark matter were like deep basins, sucking in matter from all around. The underdense areas, the places with less dark matter, could not hold on to their material. They gradually leaked and emptied out, leaving behind hollowness. Matter kept flowing away, pouring into the great filaments and clusters, while the voids grew larger and darker. In this way, the cosmic web was sculpted, glowing highways of galaxies separated by immense stretches of almost pure emptiness. The Bootes void is one of the most dramatic examples. It likely began as a part of space with far less dark matter than its neighbours. Over billions of years, as gravity funneled material into the richer areas, this region was left behind, stripped nearly bare of both dark and ordinary matter. Today, it stretches across hundreds of millions of light years, a colossal cavern of space that feels haunting in its silence. It stands as a ghostly monument to the subtle yet commanding hand of gravity and the unseen power of dark matter. Although we cannot see dark matter directly, it is the quiet architect of all that exists. It built the galaxies, traced the filaments, and hollowed out the voids. Without it, there would be no grand design, no cosmic tapestry of light and shadow. Even inside the Bootes void, where emptiness seems overwhelming, dark matter has not disappeared entirely. It is still present, though spread much more thinly than in most of the universe. While this void may look like a yawning black gulf, it is not perfectly hollow. It simply has far less dark matter and ordinary matter compared to the busy regions of the cosmic web. In dense clusters of galaxies or along the sprawling filaments, dark matter clumps more tightly. This concentration creates powerful gravitational fields, which in turn pull in gas, stars, and galaxies. These places are bustling crossroads of the cosmos. By contrast, in voids, the dark matter is stretched thin and scattered like dust across a vast plain. Here, gravity's pull is weaker, almost gentle. This difference has a huge effect on the galaxies that happen to find themselves in a void like Bootes. These galaxies are rare and lonely, like tiny islands stranded in a wide, still sea. Unlike their cousins in crowded galaxy clusters, they do not feel the constant tug and push of nearby structures. Instead, they drift quietly, evolving in isolation, far removed from the busy traffic of cosmic life. Even so, these galaxies are not completely defenseless. Each one still has its own small halo of dark matter. This halo acts like invisible glue, binding its stars and gas together. Without this hidden skeleton, the galaxies would fall apart under the pressure of cosmic expansion. But they remain intact, floating peacefully in their wilderness surrounded by vast silence. The existence of even a thin layer of dark matter in voids reminds us that no corner of the universe is untouched by it. From the densest clusters to the loneliest voids, dark matter weaves its web everywhere. It is the hidden thread that ties the cosmos together. On the largest scales, this invisible web becomes even clearer. The cosmic web is not made of galaxies alone. The glowing points of light we can see are only the surface decoration. Beneath it all lies an immense skeleton of dark matter. The voids are the cosmic valleys where this hidden fabric has been stretched thin, and the filaments are the ridges where it gathers most strongly. Scientists have tested this idea using powerful computer simulations. These programs attempt to recreate how the universe grew from the Big Bang, which happened more than 13 billion years ago. The results are astonishing. Only when dark matter is included in the equations do the simulations produce the intricate web of filaments, clusters, and voids that we actually observe. When scientists try to model the universe using only ordinary matter, the picture falls flat. Instead of a rich textured tapestry, the universe in those models looks dull and uniform, lacking the vibrant structure we know to be real. This close match between simulations that include dark matter and telescope observations is one of the strongest pieces of evidence we have that dark matter is real. It is not just a guess or a convenient story, it is an essential ingredient in the recipe of the universe. Even the Bootes void itself, a bubble of near emptiness spanning hundreds of millions of light years, is proof of this. It demonstrates that dark matter is not only responsible for creating brilliant galaxies, but also for carving out the haunting silences between them. It shows that the universe is shaped not just by what is present, but also by what is absent. In this way, dark matter is like an invisible artist. With one hand, it paints the stars, galaxies, and filaments in bright strokes of light. With the other, it shapes the dark, vast spaces in between, using emptiness as part of its masterpiece. By studying voids, astronomers are peering into the shadowy brushstrokes of this unseen artist, trying to learn how the grand cosmic design came to be, both the glowing peaks of creation and the silent valleys of absence. The most important way to measure and map such cosmic gaps, like the Bootes void, is something called a galaxy redshift survey. Think of it like this. Imagine you're standing in a thick, foggy forest. You can't see the whole forest, only the trees. To really understand the shape of the forest, you need to know where each tree is, not just side to side, but also how far away each one is from you. That way you can build a full three-dimensional picture. In space, galaxies are like those trees. We can see where they are in the sky, like dots on a flat map. But to understand the real shape of the universe, we need to know how far away each galaxy is. Only then can we build a three-dimensional map, one that shows not just galaxies, but also the giant empty spaces between them. This mapping process starts with very strong telescopes. These aren't just big versions of the telescopes you might use in your backyard. They are highly advanced tools built to collect the faintest bits of light coming from galaxies unimaginably far away. Some of the biggest and best ground telescopes are found in places with clear and dark skies, like the dry deserts of Chile, home to the European Southern Observatory's Very Large Telescope, or VLT, or on the high mountains of Hawaii, where the Keck Observatory stands. These telescopes have mirrors that are many meters wide, made to gather as much light as possible during long nights of watching. But that's not all. Space telescopes like the famous Hubble Space Telescope and the newer and stronger James Webb Space Telescope also play an important role. Floating high above Earth's air, these space telescopes are free from the blurring effects of wind and weather. They act like giant cosmic buckets, catching ancient light that has travelled across the universe for hundreds of millions or even billions of years. Once a telescope catches the light from a faraway galaxy, that light is sent through a special tool called a spectrograph. A spectrograph is like a very advanced prism. It splits the light into its different colours, much like how sunlight becomes a rainbow after shining through raindrops. But instead of just making a pretty arc of colours, the spectrograph shows a detailed barcode-like pattern, a spectrum, full of dark and bright lines. These lines are extremely important. They are the unique fingerprints of the elements that exist in the galaxy. Every element in the universe, like hydrogen, helium, or oxygen, leaves a special mark on light. For example, hydrogen, which is the most common element in space, always shows up with the same exact pattern. When astronomers look at the spectrum of a faraway galaxy, they search for these well-known fingerprints. Now comes the key part. If a galaxy were not moving compared to us, the lines would appear exactly where we expect them to be. But the universe is growing. This means nearly all faraway galaxies are moving away from us. When a light source moves away, the light waves stretch out, just like the sound of a train whistle drops in pitch as it speeds away. As light waves stretch, their colour shifts toward the red end of the spectrum. This stretching of light is called redshift. The more the light is stretched, the more redshifted it becomes, and the faster the galaxy is moving away. Astronomers can measure exactly how much the lines in the spectrum have shifted, and from that they can work out the galaxy's speed and distance. Thanks to the work of astronomer Edwin Hubble, we know that the farther away a galaxy is, the faster it seems to be moving away. This rule is called Hubble's law, and it gives us a cosmic measuring stick. In other words, redshift tells us how far away a galaxy really is. By measuring the redshift of thousands, even millions of galaxies, astronomers can build a huge three-dimensional map of the universe. This map shows where galaxies are packed closely together in long strands, where they form giant superclusters, and most importantly, where they are not. Those vast and spooky empty regions like the Booty's Void. To figure out the size and shape of Booty's Void, astronomers must gather a huge amount of information, especially something called redshift data, from not just thousands, but often millions of galaxies spread across wide parts of the sky. But this is no quick task. It takes years of hard, patient work and the efforts of many scientists. Giant sky surveys such as the Sloan Digital Sky Survey, often called SDSS, and the 2-degree Field Galaxy Redshift Survey, known as 2DFGRs, were made for this exact purpose. These are huge science projects that involve teams of researchers working over long periods of time, sometimes decades. They scan large parts of the night sky step by step, gathering light from hundreds or even thousands of galaxies at once. They do this using special instruments that break down the light from each galaxy into its different colours. This is called taking a spectrum. From the spectrum of a galaxy, scientists can figure out two very important things. First, they find out exactly where the galaxy is in the sky, its two-dimensional spot. Second, they measure how much the galaxy's light has been stretched, or redshifted, as the universe grows. This redshift tells us how far away the galaxy is. When you put together the position and the redshift of millions of galaxies, you get something amazing, a three-dimensional map of the universe. On this map, each galaxy becomes a tiny glowing dot. And when you look at all those dots together, a grand structure starts to appear. You see long, thread-like strands of galaxies, called filaments, stretching across space. At the points where several filaments cross, you find thick clumps of galaxies called clusters. But most fascinating of all are the vast, wide regions where galaxies are missing. These are the voids, and among them, the Bootes void stands out as one of the largest and emptiest ever found. But finding a void like the Bootes void is not as simple as spotting a black hole or a planet. There is no solid edge or clear line that marks where it starts or ends. Instead, astronomers rely on smart computer programs and math methods to spot these strange regions. They look for places in their galaxy maps where the number of galaxies suddenly drops far below what is expected. It's not just about spotting a gap, it's about measuring just how empty that gap really is. To picture this, think of plotting every galaxy as a small dot on a computer screen. In most parts of the universe, the screen would be filled with dots, some packed tightly together, others more spread out. But in a cosmic void, you would see huge blank spaces with very few or no dots at all. The Bootes void shows up on these maps as one of the most powerful examples of emptiness, a vast cosmic bubble where galaxies are extremely rare. Scientists can even work out just how empty it is by comparing its galaxy number to the average number in the universe. This measure is called the density contrast, and in the case of the Bootes void, this contrast is extremely high. That means it is not just a little empty, it is one of the most underfilled regions ever found in space. To better understand the size and shape of such voids, astronomers use a clever method called percolation analysis. This method is a bit like watching how water flows through a sponge. Just as water finds its way through all the small holes and paths in the sponge, this method helps scientists see how large empty spaces in the universe are linked. The edges of these voids are not sharp. They don't have walls. Instead, the emptiness slowly fades into the surrounding filaments and galaxy clusters. So the Bootes void is not a perfect sphere. It is more like a huge bubble, shaped by the pull of the heavy cosmic structures around it. It is as if matter has been drawn away from this central region and gathered to form the walls of the cosmic web. One of the most interesting challenges in studying the Bootes void is looking at the rare galaxies that actually live inside it. These are sometimes called lonely galaxies because they exist in isolation, far from the crowded, busy areas where most galaxies live. Their existence proves something important. The Bootes void is not completely empty. It is just incredibly bare. But these lonely galaxies are very hard to see. They are extremely far away and often very faint, since they are not making stars as actively as galaxies in thicker regions. To study them, astronomers need to use strong telescopes and watch for long periods of time to collect enough light. When they measure the redshift of these galaxies, they can confirm that the galaxies truly lie within the Bootes void and are not just lying in front of or behind it by chance. And by studying their shapes, the rate at which they make stars, and the amount of gas they hold, scientists can learn how galaxies act in these calm, gravity-quiet places. These isolated galaxies are like natural experiments. They help us see what happens when a galaxy grows up all alone, untouched by the pull and fights that happen in crowded cosmic neighborhoods. Looking ahead, the future of void studies is very exciting. New tools are being built that will allow astronomers to map the universe even more clearly. Upcoming galaxy surveys will be able to see fainter and more faraway galaxies than ever before. They will cover much wider parts of the sky and detect millions of galaxies, helping us sharpen our three-dimensional maps of the universe. Some of these new instruments can see light not just in the visible range, but also in the infrared. This is important because infrared light can pass through space dust, showing galaxies that were hidden before. These tools may even reveal more lonely galaxies hiding inside the Bootes void. In addition, new computer programs and artificial intelligence are being made to sort through the huge piles of data these surveys will create. These tools will help scientists quickly find and study the complex patterns in the universe, including voids and filaments. Even the faint leftovers of the cosmic microwave background, the ancient light left over from the Big Bang, can help tell us more about voids. As this light travels across the universe, it passes through different cosmic landscapes. When it moves through a huge void like Bootes, its path is slightly changed, creating a tiny cold spot in the cosmic background. This faint effect is known as the integrated Sachs-Wolf effect. Though extremely small and hard to see, these cold spots can give scientists yet another clue about the presence of large voids, proving their effect on the universe's structure.